There are things so constantly present that we eventually stop seeing them. Water is one of them. It sits in the glass, in the clouds, in the rivers, in the pipes, in the cells. It cools engines, softens landscapes, carries heat, dissolves minerals, shapes the weather, and quietly keeps life going. It may also be the first substance most people learn to name, yet one of the last they think to question. And that is precisely where water begins to become strange. A substance so familiar it seems fully understood, yet it keeps behaving against intuition. In its solid form, it floats instead of sinks. In its liquid form, it holds heat far more stubbornly than many similar substances. Its molecules cling to one another, line up, rearrange themselves, and coordinate in ways that do not easily collapse into any simple explanation. What I find remarkable is this: after centuries of careful measurement, precise experimentation, and powerful simulation, water still occupies a very unusual place in science, not completely unknown, and not mysterious in any dramatic sense, but unfinished. It has been examined from nearly every possible angle, by chemists, physicists, biologists, and planetary scientists. Measured, modeled, frozen, boiled, compressed, stretched, illuminated, and simulated in extraordinary detail. And yet, at the most fundamental level, liquid water remains one of the hardest everyday materials science has ever tried to fully describe. It is exactly that tension between the familiar and the incomplete that this film wants to enter. Not water as a symbol, a metaphor, or a miracle, but water as a real physical system, governed by simple rules that somehow produce behavior of astonishing richness, a substance that once helped science learn how to measure the world, and that still reminds science of its own limits. So the journey here will not rush toward a neat conclusion. It moves slowly, from what is firmly known to what is still debated, from structure to behavior, from molecule to planet, from certainty to open questions. It is simply an invitation to look more closely at why something so ordinary can still remain so unfinished. Welcome to The Sleepy Scientist. If you enjoy this kind of calm, reflective science, consider liking the video and subscribing to the channel. And if you are listening or watching from somewhere right now, you can also share where you are, a place shaped by the ocean, by rivers, by rain, or simply a place where a quiet glass of water is sitting nearby. What is interesting is that water entered the history of science in a very quiet way as well. Long before laboratories looked like laboratories before instruments, standardized units, glassware, or calibrated scales, people already needed some way of understanding matter that could be compared, repeated, and trusted. And water, simply because it was everywhere and behaved with enough consistency, became one of the first substances that helped human beings learn how to measure the world. In the ancient Mediterranean world, water was grouped with earth, air, and fire as one of the classical elements. At that time, it was not seen as a substance with internal structure, but as a basic category of existence. Water was simply water, wet, flowing, heavy, naturally seeking its own level, useful, familiar, and philosophically complete. It was a powerful way of thinking, but it also placed limits on curiosity. Once water was already an element, there was little reason to ask how it operated internally or why its properties were so stable. Meaning mattered more than measurement, and explanation mattered less than classification. Centuries later, a different approach began to take shape, especially in the scientific traditions of the Islamic Golden Age. Across a landscape of knowledge stretching from Central Asia to the Eastern Mediterranean, scholars began to see water not as a philosophical premise, but as a physical substance that could be quantified, compared, and tested. Around the year 1000, Al-Biruni carried out very careful measurements of density, using water as a reference standard. He compared the masses of equal volumes of materials by observing how much water they displaced, and obtained values that were astonishingly accurate by modern standards. That was no longer abstract philosophy, that was experimental method. Along the same movement, Ibn Sina, known in the West as Avicenna, approached water from the perspectives of medicine and physics. He described water's role in bodily processes, its effect on temperature, and its ability to dissolve other substances. In this view, water was something whose properties could be observed, not something simply accepted as self-evident. Heat transfer, purity, and interaction with other materials became practical questions rather than merely philosophical ones. And perhaps the most important part of that shift was not that they had decoded the nature of water, they had not, but that water began to become a stable point of support, a reference standard trustworthy enough for other measurements to be built around it. The strange thing is that, for a very long time, water did not sit at the center of science as a question, but as a point of support. It became the thing people held onto whenever they wanted to make the world a little less uncertain, a substance stable enough to serve as a reference, familiar enough to be repeated, reliable enough to turn error into something manageable. And so water gradually took on a quiet but foundational role, not the thing to be explained first, but the substance that made other things measurable. As experimental science developed in early modern Europe, that role only grew. The first, temperature scales were anchored to water's phase transitions. Its freezing point and boiling point, under standard atmospheric pressure, became fixed markers. Not because water was thought to be special in any cosmic sense, but because it was available, reproducible, and stable enough to be useful. Alongside temperature, the concept of purity was also repeatedly defined in relation to water. Distillation techniques were refined to produce ever purer samples of water, and when a laboratory could remove dissolved salts and impurities from water, that almost also proved it had the ability to purify other substances. Even mass, at one point, passed through water in search of its own standard. Early definitions of units, such as the gram, were tied to the mass of a specific volume of water at a specific temperature. Here, water was not the object being analyzed. It was the ruler. A ruler so quiet that one easily forgets it shaped the very way science learned to operate. It accustomed science to the idea of repeatability. It nurtured the belief that nature could be standardized, that a measurement made in one place could still be trusted elsewhere, so long as both were based on the same reference substance. Even when chemistry matured and the theory of the classical elements was abandoned, water did not lose its central place. In the late 18th century, when Lavoisier helped lay the foundation for modern chemical nomenclature, water was no longer regarded as an element. It was recognized as a compound, hydrogen and oxygen combined in a fixed ratio. That was a transformative shift. But rather than diminishing water's status, the discovery made it even more important. Water began to reveal something deeply powerful. Complex behavior could arise from simple ingredients. Two light gases could combine to produce a stable liquid, one that could flow, freeze, boil, dissolve salts, and support life. And yet, at that time, people still underestimated the complexity inside water. Early atomic models often imagined molecules as rigid objects, fixed bonds, stable structures. Water, therefore, looked rather tidy when placed in a diagram or an equation. But liquid water is not a crowd of isolated molecules standing apart. It is a constantly shifting network, where bonds are continuously stretched, bent, broken, and reformed on timescales far shorter than human perception. There is structure there, but only briefly. There is order, and then the order disappears. There is a very subtle paradox here. Precisely because water was so useful as a standard substance, it became easier to believe it had already been fully understood. That assumption quietly lingered behind many of science's advances. Throughout the 19th century, water continued to underpin a host of new techniques. Calorimetry depended heavily on it because of its great capacity to absorb energy without changing temperature too quickly. In laboratories, reactions were heated and cooled in water baths. Samples were stored, diluted, and transported in aqueous solutions. Biological research needed water to keep tissues alive. Geological research used flowing water to model erosion and sediment transport. In all of those cases, water was the medium, the backdrop, the default constant. And for that very reason, it began shaping habits of thought as well. Instruments were calibrated against water. Procedures were designed with the properties of water as a premise. Gradually, an expectation took form that liquids in general could be treated in similar ways, that their behavior could be averaged out, smoothed over, and simplified. Only later did it become clear that water was not at all a typical representative of liquids in general. Many of the qualities that made it so useful were also exactly what made it unusual. Its density anomaly, in which the solid is less dense than the liquid, is rare. Its surface tension is unusually high. Its heat capacity exceeds that of most similar substances. Its ability to dissolve ionic and polar compounds is also exceptionally strong. Each of those individual properties was known, but their deeper origin was not pursued with any real sense of urgency. After all, water still did its job too well. Looking back, what emerges is a layer of irony, gentle but profound. Water taught science how to measure, standardize, and control the physical world. It trained generations of researchers to trust in the consistency of experiment. It anchored definitions of temperature, mass, and purity, and in a very practical sense, it helped make the modern laboratory possible in the very form we recognize today. There is something almost paradoxical in the history of studying water. The very thing that made people trust it most also helped conceal what they did not yet understand about it. Water helped science develop confidence, yet at the same time it quietly refused a complete description. So, this is not exactly a story of ignorance. It is more like a story in which success, if sustained long enough, begins to create blind spots. Water did not merely shape the way people thought about matter. It also helped define what counted as a good experiment, what kind of data was considered trustworthy, and what kinds of complexity was seen as worth confronting. Only much later did researchers gradually begin to realize that the very substance they relied on most might also be the one that challenged their assumptions most deeply. That realization did not arrive as a flash of illumination. There was no single discovery that suddenly overturned everything. It came slowly, through small discrepancies, recurring anomalies, and models that worked almost perfectly yet always fell just a little short. In a sense, water performed its role too well. It taught science how to measure the world before science was truly ready to measure water itself. At first glance, this should have been an easy problem. Just 2 hydrogen atoms and 1 oxygen atom. A structure small and compact, with no long chains, no branching, no exotic elements. Set beside the enormous molecules of biology or the complex crystal lattices of solid materials, water looks rather modest. It seems like the kind of system whose secrets ought to be peeled away layer by layer without too much difficulty. And for a long time, scientists genuinely expected that to be the case. In classical chemistry, molecules were often imagined as tiny mechanical objects. Atoms were like beads, linked together by rigid joints. Once the parts were clear, the behavior of the whole seemed as though it should follow naturally. That way of thinking worked surprisingly well for many substances, especially gases, where interactions are weak and fleeting. It also worked well enough for solids, where atoms merely vibrate around fixed positions. But water began resisting that neatness the moment people tried to pull it down to the atomic scale and describe it there. In the early 20th century, chemistry and physics passed through a quiet but profound transformation. Classical ideas of atoms and bonds gave way to quantum mechanics, where certainty was replaced by probability, and rigid orbits were replaced by a more wave-like kind of behavior. Chemical bonds were no longer just connections. They became shared states, governed by the mathematics of quantum theory. Among those who helped shape that turning point were Walter Heitler and Fritz London. In 1927, they published work explaining chemical bonding in quantum mechanical terms, showing that electrons could be shared between atoms in a stable configuration. From there, the foundations of modern molecular theory began to take shape. At first glance, Water seemed to be one of the simplest test cases for that new theoretical framework, but trouble appeared almost immediately. The bond between oxygen and hydrogen does not share electrons evenly. Oxygen pulls on them more strongly, creating an uneven distribution of charge. And that very imbalance gives the water molecule a persistent polarity, one side slightly negative, the other slightly positive. At the level of a single isolated molecule, things were still manageable. Its polarity could be measured, its bond angle calculated, its energy estimated. Quantum chemistry handled this part of the problem fairly well. But water does not exist as lonely molecules. A glass of water contains not a few molecules, but on the order of 10 sextillion of them, that is, a 1 followed by 22 zeros. Each of those molecules interacts with its neighbors through electrostatic attraction, repulsion, and short-range quantum effect. No single interaction is overwhelmingly strong, but there are so many of them that together they determine the behavior of the entire liquid. This is where classical intuition begins to lose its footing. In simpler systems, understanding the parts often leads rather directly to understanding the whole. Double the number of molecules, and many properties double as well. Add energy, and the temperature rises in a predictable way. Linear relationships like these are comforting to scientific thought. They scale neatly, smoothly, controllably, but water does not follow that path. A small change at the molecular level can produce a large non-linear effect at the macroscopic level. Cool it slightly, and it may expand instead of contract. Add heat, and its temperature does not rise as efficiently as it does in many other liquids. It is here that water's apparent simplicity begins to crack, and a system that seemed compact reveals a depth far more difficult to tame. Perhaps the most important place to begin is not with each individual water molecule, but with the fact that they are never truly alone. Water retains its appearance of simplicity only until the moment it comes into contact with itself. Once that happens, everything changes. The behavior of the system is no longer a mechanical sum of its parts, because the interactions between the parts begin to matter just as much as the parts themselves. In physics, this is what is called the many-body problem. With two bodies such as a planet orbiting a star, the equations can be written down and solved exactly. With three bodies, the solutions already become unstable, sensitive to initial conditions. And once the number grows very large, exact solutions nearly disappear. What remains are patterns that can only be grasped statistically. Liquid water lies squarely in that difficult domain, and at an almost overwhelming scale. Each water molecule forms temporary bonds with several neighbors through hydrogen bonding. These bonds are weaker than covalent bonds, but they are directional, and more than that, they are cooperative. One bond forming can alter the likelihood that other bonds will appear nearby. So in liquid water there is no fixed order, only networks that continually appear, dissolve, and reappear on timescales of mere trillionths of a second. At any given moment, within this liquid there are fleeting regions that resemble ice, other regions that look more like disordered liquid, and every transitional state in between. They are small, short-lived, and almost impossible to grasp through ordinary intuition, and yet they are enough to influence density, viscosity, heat capacity, and even the way sound and light move through water. Seen from afar, the surface of water feels smooth and uniform, but on the molecular scale, it is anything but still. It is restless, constantly rearranging, constantly renegotiating its own structure. And what is remarkable is that this restlessness is not meaningless noise. It is structure in motion. Modern science can describe the interactions among a few molecules quite accurately through quantum chemistry. It can also use statistical mechanics to capture the average behavior of vast numbers of molecules at once. But the hardest part lies in the bridge between those two domains, where individual quantum interactions gradually condense into the collective properties we observe at the classical scale. It is on that bridge that the simplicity of a molecule no longer guarantees the simplicity of the whole system. The laws do not disappear. They layer, multiply, and begin to produce something larger than themselves. A single water molecule, in isolation, behaves one way. Place it in a cluster of molecules, and the electronic environment around it changes. Place it in a dense body of liquid, and it becomes nearly impossible to separate its identity from its surroundings. From this point on, properties that belong to individual molecules give way to properties that exist only at the level of the network. Perhaps that is why liquid water, in the deeper sense, is not really an object, it is a process. And that too marks a shift in the way science looks at matter. Instead of asking only what a molecule is, one is forced to ask how molecules coordinate with one another, how patterns emerge from interaction rather than command, and how order appears without any pre-existing blueprint. Water was one of the first substances to force science toward that realization. It is too strange to be explained if each molecule is treated as an independent actor. It compels attention to correlation, fluctuation, and collective motion. And there is a very quiet lesson here. Nature does not promise that small causes will produce only small effects, nor does it guarantee that understanding all the individual pieces will automatically yield an understanding of the whole picture. With only 2 hydrogen atoms and 1 oxygen atom, a system can already arise that resists every overly neat explanation, not because it is exotic, but because it is too deeply bound to itself. That is not a failure of science. It is more like a boundary condition, a reminder that as the degree of cooperation increases, predictability begins to fade. Even at the smallest scale, water already carries an asymmetry within it. Oxygen pulls the shared electrons more strongly than hydrogen does, leaving one side of the molecule slightly negative and the other slightly positive. This is not the kind of full charge seen in ions, but only a partial charge. Yet that is enough to turn the water molecule into a dipole, a structure with an inherent direction and orientation. On its own, that detail might not seem especially striking, since many other molecules also have uneven charge distributions. What makes water different is that when countless such molecules are placed close together, those dipoles begin to interact very strongly. And in liquid water, no molecule stands outside that network. Every molecule is surrounded by others, all carrying their own charge asymmetry. What makes water different is not merely that each of its molecules carries an uneven charge distribution, but that this imbalance never remains still in relation to the others. In liquid water, every dipole is constantly sensing the dipoles around it. They rotate, shift, and continuously reorient themselves in response to the local electric fields created by nearby molecules. Out of that sensitive network emerges a very important property: dielectric behavior. Put simply, this is a material's ability to weaken the electric force between charged particles, and water does this exceptionally well. Its dielectric constant is higher than that of most liquids, which means that charges inside water no longer feel one another as strongly as they would in air or in a vacuum. But that screening is not an unmoving cushion. It is produced by motion. When a charged particle appears in water, the surrounding molecules rotate so that the end carrying the opposite partial charge points toward it. In doing so, they partially cancel the original electric field. The charge does not disappear, but it becomes wrapped in a responsive cloud of dipoles, making the field softer, more spread out, less severe. In the mid-20th century, Lars Onsager explored this kind of behavior in depth. He developed theoretical descriptions of dipoles in polar liquids and showed that long-range interactions are not simply the consequence of isolated charges, but of a collective response involving many molecules at once. That changes the way water ought to be understood. It is not an inert backdrop. Water molecules do not merely stand there while reactions unfold in front of them. They rearrange themselves in response to the environment, and that very rearrangement alters the forces at work within the reaction. Water does not merely contain chemistry. It intervenes in chemistry. Ions dissolve in water because this liquid can stabilize separated charges. Positive and negative ions are not pulled apart by anything mysterious, but by the energetic advantage gained when each ion becomes surrounded by dipoles whose opposite ends turn toward it. This screening effect lowers the energetic cost of separation. and so dissolution becomes favorable. Acids and bases also change when they are in water according to the same logic. Protons do not wander freely. They move through a constantly restructuring hydrogen bond network, hopping from one molecule to another in a process known as proton transfer. Here, water does not stand outside the process. It participates directly, reorganizing itself to allow that motion to occur. Even neutral molecules do not escape its influence. Polar compounds dissolve easily because their charge distributions can align with the orientation of surrounding water molecules. Non-polar substances struggle more because they disrupt the local dipolar organization without offering back any compatible mode of interaction. So at a deeper level, water is more like a collaborator than a container. This is a clear departure from the older chemical view, in which a solvent was often treated merely as background condition, something that provided space, enabled mixing, stabilized temperature, but did not truly participate in the reaction pathway. Water does not allow that simplification. Because of its polarity, every reaction taking place within it is embedded in an electric environment capable of responding. The forces within that environment can be screened, amplified, redirected, and reshaped by the surrounding liquid itself. When that happens, energy surfaces change, transition states shift, and reaction rates adjust accordingly. The medium no longer stands outside the mechanism. It becomes part of the mechanism, and this extends beyond the scale of any single reaction. Because dipoles in water can influence one another across relatively long distances, patterns of orientation can propagate through the liquid. They are fleeting, but not meaningless. They help shape bulk properties such as viscosity, surface tension, and the way water responds to external fields. Onsega's work emphasized a beautiful point here. Long-range order does not necessarily require a rigid structure. Molecules do not need to be locked into place in order to influence one another. Statistical alignment is enough. That may also be why water can behave coherently without being a solid. At any given moment, within liquid water, there are regions where dipoles are to some extent aligned in a particular way. These regions form and dissolve continuously, shaped by temperature, pressure, dissolved substances, and even nearby surfaces. No region lasts for long, but taken together, they produce exactly the behavior we recognize as water. The result is a liquid that does not merely exist, but responds. Add salt, and water immediately reorganizes itself to stabilize the ions. Water is never simply present. Change the surrounding conditions, and it responds at once. Add heat, and the orientation among its molecules begins to loosen under thermal motion. Place it in an electric field, and the dipoles turn together. Bring it near a surface, and the molecules closest to that surface begin to favor certain orientations. At this point, I think it becomes hard to call water indifferent. It reacts, and it is precisely that sensitivity that allows it to support complex systems without causing them to fall apart. In biology, this becomes especially clear. Charged groups on proteins can remain stable because water softens interactions that would otherwise be strong enough to destroy structure. Biological membranes form in part because water reorganizes itself around nonpolar regions in a way that almost forces them together. No purpose, no design, just polarity, combined with density and motion, and organizing effects begin to emerge. What is remarkable is that this same underlying property connects phenomena across vastly different scales. An uneven distribution of charge within a single molecule can ultimately help govern oceans, cells, clouds, minerals, neural signaling, and even the activity of enzymes. The bridge between the microscopic world and macroscopic order here is anything but linear. A very small change in orientation can lead to a major shift in behavior. Temperature is a fairly clear example. As thermal motion increases, dipoles struggle more to maintain alignment, dielectric screening weakens slightly, and reaction rates shift along with it. All of that can be measured, even predicted in a broad sense. But to calculate it precisely remains difficult, because what is operating is not a fixed structure but collective motion. Perhaps that is why water often resembles a responsive fabric more than a stationary material. It stretches, relaxes, and then redistributes force in a dynamic way. It does not merely transmit interactions through itself. It modifies those interactions even as it transmits them. Once seen in that light, treating water as a passive background becomes inadequate. It is not a neutral stage on which chemical reactions simply take place. It is an active participant, altering what can happen. The charge imbalance within each tiny molecule is amplified into an imbalance spread across the entire liquid. Within it, order and disorder coexist. Stability emerges from motion itself. Screening arises from responsiveness. Polarity, then, does not merely explain why water dissolves salt or conducts electricity weakly. It also explains why water can organize systems without requiring a rigid framework, why it can sustain complexity without freezing into a fixed form. That charge asymmetry never truly disappears. It persists, fluctuates, propagates, and because of that, a molecule that seems simple can become a medium powerful enough to shape entire large-scale systems. That is not a flaw in water. It is the source of its quiet influence, which, once noticed, becomes very hard to stop seeing. But that strange power of water does not come from sheer strength. It comes from cooperation, and at the center of that cooperation is the hydrogen bond, a subtle interaction, weaker than the bonds that hold atoms together within a molecule, yet far more influential than its modest appearance would suggest. In water, hydrogen bonds are present almost everywhere, almost all the time. The slightly positive hydrogen atoms of one molecule are attracted to the slightly negative oxygen atom of another, and because a water molecule can form several such bonds at once, the whole liquid begins to cohere into loosely connected clusters, enough to suggest structure, but never still long enough to harden into a fixed form. At first, researchers tried to understand this phenomenon by looking at individual bonds one by one. Linus Pauling helped clarify how hydrogen bonding arises from electronic structure and why it prefers certain directions. That work was crucial because it turned hydrogen bonding into a real, measurable interaction rather than some vague form of attraction. But a limit soon became clear. Understanding a single bond still did not tell us what would happen when trillions of bonds were operating together inside a body of water. In the 1930s, Bernal and Fowler tried a different approach. They did not treat liquid water merely as disordered ice or as a compressed gas. They proposed that liquid water had its own kind of organization, not fixed, not crystalline, but patterned. In that view, liquid water contains networks of molecules connected by hydrogen bonds, and these networks are continually forming and breaking apart, constantly rearranging under the influence of thermal motion. There is order there, but it is an order of probability rather than deterministic order. That distinction matters greatly. If a system is deterministic, then, in principle, knowing the exact state of every part allows one to infer the state of the whole. But if a system is statistical, what can be predicted is only likelihood, only average behavior over time. Individual configurations are too short-lived. Liquid water belongs firmly to the latter category. At any given moment, a molecule may be bonded to several neighbors, to only one neighbor, or to none at all. That structure changes on timescales of trillionths of a second. Bonds stretch, rotate, break, and then reform elsewhere. No single shape is sufficient to represent the whole liquid. What remains is continuous turnover, and it is from that turnover that water's behavior emerges. This is what people mean when they speak of fluctuating order. There is structure, but it is not fixed in space. There is organization, but it does not endure through time. The pattern exists more as a tendency than as a blueprint. Sometimes people like to imagine the hydrogen bond network as a loose scaffold filling the water. That image is not wrong, but it is still too static. It may be more accurate to think of it as a field of interactions that is constantly reconfiguring itself. Every new bond that appears changes the likelihood that other bonds will form around it. Once a molecule has entered into one bond, its angles shift, its charge distribution adjusts slightly, and its local environment changes with it. So hydrogen bonding in water is not a chain of isolated events. It is a collective phenomenon. It is precisely because of that collective nature that the network can respond so flexibly to changing conditions. Raise the temperature, and thermal motion disrupts alignment. Bonds become shorter-lived, and the average connectivity declines. Lower the temperature, and bonds last longer. The network spreads further. As water approaches freezing, it begins to take on ice-like character, not suddenly, but gradually, as local order becomes more pronounced. Pressure acts in its own way. Compressing the liquid squeezes the open structures that hydrogen bonding tends to favor, forcing other arrangements to appear and shifting the balance. Dissolved substances interfere with the network as well, bending it, sometimes stabilizing certain forms of organization, sometimes disrupting them. Water does not resist in a rigid way. It adapts by rearranging its own bonding patterns to accommodate new arrivals. That may also be why water can dissolve so many substances without losing its own identity. What is astonishing about water is that it can be disturbed without falling apart. Its hydrogen bond network absorbs disturbance in a remarkably soft way. It bends, shifts, rearranges, and then continues to exist. There is no instruction manual standing behind it, telling water how it ought to organize itself. There is no master diagram, no global pattern imposed in advance. There are only very local interactions, repeated over an enormous scale, and from that a collective behavior gradually emerges. It is perhaps here that many of water's most familiar properties begin to find their explanation. A boiling point unusually high for such a small molecule, a surface tension strong enough to pull the molecules at the outer layer inward, and a high heat capacity, because the energy supplied does not merely increase motion, but must also be used to rearrange bonds. But the cooperation that gives rise to those properties has never been perfect. It is noisy, intermittent, incomplete, and always fluctuating. And that is precisely the essential part. If the hydrogen bond network ever reached perfect order, water would become solid. If it lost all order entirely, it would behave like a gas. Liquid water exists in the narrow region between those two extremes, held there by motion itself. This is also why mathematics struggles to capture it. A model must preserve directionality, fluctuation, and the correlations among vast numbers of molecules. Simplify too much, and the network disappears. Include too much detail, and the calculation becomes unmanageable. The important insight Bernal and Fowler left behind was not that they found the exact structure of liquid water, but that they forced science to change the very meaning of structure. Order in a liquid could no longer be described in terms of fixed positions or repeating units. It had to be understood in terms of probability and correlation. From that shift, a broader scientific idea opened up: emergence. This is what happens when complex behavior appears out of simple rules without any central controller. The properties of the whole system can no longer be easily inferred from the properties of the individual parts, because what matters now is interaction, feedback, and scale. Water is almost a model example of this. A single hydrogen bond is weak and short-lived, but a vast population of such bonds creates stability, coherence, and adaptive resilience. That is how water can both flow and resist compression, both change and retain its identity, both support life and remain chemically neutral. The network does not have one fixed shape, but its influence is everywhere. It may be easier to picture this if one does not think of the hydrogen bond network as a structure, but as a field. A field is defined not by fixed objects, but by relationships. It changes smoothly across space and time, responds to disturbance, and transmits influence without requiring rigid connections. In water, the hydrogen bond field is everywhere. It is the medium through which forces propagate and patterns arise. Because of that, a small local change can still produce consequences across the whole system. What matters most is not that a single molecule joins or leaves the network, but how that change spreads outward, quietly shifting the probabilities of countless nearby interactions. Seen this way, attention naturally moves away from isolated molecules and toward collective dynamics. Correlation lengths, fluctuations, timescales, cooperative motion, and that is also why water keeps surprising us. Systems governed by emergence are not lawless, they are simply not obvious. The large-scale behavior may be predictable, but the details are always more tangled than expected. There is a very humbling lesson here. Water does not hide its secrets in chemically complicated ingredients. It hides them in cooperation in the fact that countless simple things acting together can generate a kind of behavior that none of the individual parts contains on its own. Hydrogen bonds, taken one at a time, are almost unremarkable, but put them together, and they form a network that is always moving, always adapting, always reorganizing, and nearly every property of liquid water is rooted there. The order this network creates is never fixed, but it never disappears either. It flashes into being and fades, flows onward and returns, keeping the liquid stable without making it rigid. And from that fluctuating order, larger properties begin to emerge, properties that no longer belong to any individual molecule, but to the system as a whole. It is perhaps at exactly that point that water's deepest challenge to understanding truly begins. Among all of water's strange habits, one stands out so plainly that everyone has seen it, yet its extraordinariness is still easy to overlook. Ice floats. In most substances, cooling means contraction. Molecules slow down, move closer together, and pack more tightly. Solids therefore usually sink in their own liquid, because the atoms have become locked into dense structures. This is almost a rule of common experience, and water breaks it. As liquid water cools from room temperature, it first behaves as expected. Its density increases as thermal motion decreases. The molecules vibrate less violently and sit closer together. But then, when the temperature comes within only a few degrees of freezing, a quiet turning point occurs. Instead of continuing to contract, water begins to expand. This is the anomalous expansion of water, one of the clearest signs that it does not behave like a typical liquid. At the freezing point itself, the effect becomes even more pronounced. When liquid water turns to ice, its volume increases by about 9%. That number may sound small, but on the scale of lakes, oceans, or planetary crusts, it becomes an immense difference. The reason lies in structure. As water freezes, hydrogen bonds become more stable and longer-lived, drawing the molecules into an open hexagonal network, whose aim is not maximum packing density, but the maximization of hydrogen bonding. Each molecule is held with its neighbors at specific angles, and that arrangement creates empty spaces within the crystal lattice. Those spaces lower the overall density. By contrast, in liquid water, because the hydrogen bond network is constantly rearranging, the molecules can on average still slip closer together. The result is that ice is less dense than liquid water. Near the freezing point, this can even be described as a kind of negative thermal expansion. Instead of contracting as it gets colder, water expands. That behavior alone is enough to place it among a small group of materials that behave anomalously under certain conditions, and its consequences extend very far. When ice floats on the surface of water, it becomes an insulating layer. Lakes and oceans freeze first at the top, while the water below loses heat more slowly and so remains liquid even when the air above has dropped far below the freezing point. This is what allows aquatic life to survive the cold season without being locked solid from surface to bottom. If ice sank, the entire logic would reverse. Bodies of water would begin freezing from below. Ice would accumulate on the bottoms of lakes and seas. Melting would become slow and incomplete, and over time many aquatic environments could become permanently frozen. A single structural anomaly is enough to shape ecosystems on a planetary scale. But floating ice is only the most visible expression of a deeper rule. Beneath it lies something even more striking. Water does not reach its maximum density at the freezing point itself, but a few degrees above it. As water cools from higher temperatures, it becomes denser until it reaches that point, and if it is cooled further, it begins to expand again. From that point of maximum density, Water begins to expand again if it is heated further. That detail alone is enough to shape the seasonal behavior of lakes and oceans. It determines how layers of water mix, with consequences for nutrient transport, oxygen distribution, and the thermal stability of the entire water column. This is not the kind of behavior ordinary intuition would easily predict, and once pressure is brought into the picture, everything becomes richer still. In the early 20th century, Percy Bridgman pushed water and ice into conditions of extremely high pressure to see how they would respond. What he discovered was that ice does not have just one face. Under increasing pressure, water forms an entire sequence of different crystalline ice phases, each with its own structure and density. Some are denser even than liquid water, others display unusual electrical or mechanical properties. Of course, those phases lie far from the everyday world of a glass of water or a winter lake, but that is precisely why they reveal something important. The structural behavior of water was never fixed. It adapts. What Bridgman truly exposed was that hydrogen bonding is not locked into a single arrangement. Depending on temperature and pressure, it can reorganize itself in fundamentally different ways. The familiar hexagonal ice in a freezer or at the poles is only one possibility among many. In some high-pressure ice phases, the molecules are packed more tightly than in liquid water. In others, the entire bonding pattern changes dramatically. So, the fact that ice floats is not an absolute rule of water under all circumstances. It is a condition-dependent outcome, arising from the structure water selects under a very specific balance of forces. And that brings us back to a central point. Water violates expectation not because it is erratic, but because it is flexible. Its behavior always depends on the balance between hydrogen bonding, thermal motion, and pressure. Change that balance, and a different structure emerges. The expansion that occurs as water cools near the freezing point follows the same logic. At higher temperatures, thermal motion is strong enough to disrupt open arrangements, allowing molecules to crowd closer together. But as the temperature drops, hydrogen bonding gradually begins to outweigh motion, pulling the structure toward a more open form and causing the volume to increase. In a sense, all of water's anomalies are woven from this tug-of-war between order and motion. Its high heat capacity, its resistance to compression, the unusual way it responds to pressure compared with most liquids, all of them bear the marks of that competition. Floating ice is simply the most visible expression. From a planetary perspective, these properties are anything but marginal. They reach deep into climate, geology, and even the persistence of liquid water on the surfaces of worlds. On Earth, floating ice regulates heat exchange between the atmosphere and the ocean. Seasonal cycles of freezing and thawing help redistribute energy. Polar ice reflects sunlight and therefore affects global temperature. Glaciers, through erosion and deposition, reshape the planet's surface over time. Even the expansion of water upon freezing plays a role in geology. When water seeps into cracks in rock and then freezes, it expands, generating enough pressure to fracture the rock, slowly helping to produce soil and remake landscapes. A quiet process, patient and immensely powerful. Beyond Earth, those anomalies lose none of their importance. On icy moons such as Europa and Enceladus, different phases of ice may exist deep below the surface under enormous pressure, and the behavior of ice under those conditions directly affects whether subsurface oceans can persist, how heat is transported, and whether chemical exchange with the rocky core below is possible. If water behaved more like a typical substance, many of those environments would likely be very different. Ice might sink, liquid layers might become much thinner, or disappear altogether. Heat transport would change. Habitability, for the same reason, would be far less likely. In that sense, the fact that ice floats is not some charming detail of nature. It is the surface trace of a deeper molecular mechanism, powerful enough to shape entire worlds. It is easy to look at that as a stroke of rare good fortune, but from a scientific point of view, it is simply a consequence of hydrogen bonding and molecular geometry. There is no need to assume any purpose. No need for any kind of special fine-tuning. What is truly astonishing is that from such simple ingredients, 2 hydrogen atoms, 1 oxygen atom, a bonding geometry that favors open structures, interactions weak enough to keep rearranging, yet strong enough to cooperate, there can emerge a substance that expands as it cools, rises when it freezes, and helps stabilize environments across countless scales. Floating ice, in the end, is only the most visible tip of a structural iceberg, hinting that the most familiar behaviors of water are really expressions of deeper, quieter laws. And those laws do not become simpler when pushed to extremes. On the contrary, they become more diverse, more subtle, and more revealing. In that way, water continues to remind science that expecting something and truly understanding it are 2 very different things. There is another expression of this strangeness, less dramatic but present everywhere: the way water handles heat. It takes in heat quietly, holds it with unusual patience, and releases it only slowly. Most materials warm up fairly quickly when energy is supplied. Their temperature rises almost directly with the amount of heat they receive. Water does not. It has an unusually high specific heat capacity, meaning that raising its temperature by 1 degree requires significantly more energy than for most other liquids. Broadly speaking, warming water by 1 degree takes several times more energy than warming ethanol or liquid ammonia by the same amount. This is not a minor detail. From the kitchen to the climate, that property nearly governs the way water behaves. And at the molecular level, the explanation brings us back once again to familiar ground: the hydrogen bond network. When heat enters liquid water, much of that energy does not go straight into making the molecules move faster. A substantial portion is held up in the continuous process of bending, breaking, and reforming the hydrogen bonds that bind the liquid to itself. There is a beautiful way to think about water. When energy enters it, that energy does not immediately turn into visible warming. First, it is used to renegotiate relationships. Hydrogen bonds bend, break, and form again. The network adjusts itself before the molecules truly begin to speed up in any significant way. That is why water's temperature seems buffered. Energy goes in, but the change does not flare up at once. Part of the heat is temporarily stored in the ever-moving structure of the liquid itself, and the thermodynamic consequences of this run far deeper than their outward quietness might suggest. In the language of entropy, water slows the pace at which disorder increases. In many other materials, adding heat means random motion rises quickly, and entropy climbs almost directly with it. But in water, a significant portion of the energy is diverted into rearranging interactions rather than being poured entirely into motion. Entropy still increases, of course, but more gradually. One might think of this as a kind of entropy buffer. Water regulates the rate at which chaos appears, and that ability alone is enough to shape climate. Large bodies of water resist rapid temperature change. The oceans absorb vast amounts of solar energy during the day and release it slowly through the night. Seasonal warming and cooling are smoothed out. Coastal regions therefore tend to have milder climates than inland regions at the same latitude, and day-night temperature swings are less severe. On a planetary scale, water helps make climate less extreme, but this does not stop at weather. Water's deeper role becomes visible in systems that are not in equilibrium. Equilibrium is the state in which energy flows have balanced out, and the system no longer changes overall. Yet the most interesting systems, living organisms, weather patterns, ecosystems, exist precisely by remaining far from that state. They continue to be what they are by constantly exchanging energy with their surroundings. Ilya Prigogine devoted much of his work to understanding such systems. He introduced the concept of dissipative structures, organized patterns that emerge and persist in systems fed by a continuous flow of energy. Convection cells, in a heated fluid, chemical oscillations, and biological metabolism are all examples. They do not maintain order by avoiding entropy, but by exporting entropy outward, preserving organization through the very act of dissipating energy. In that picture, water plays an almost foundational role. Because it can absorb and release heat without producing large swings in temperature, it creates a thermal environment stable enough for far from equilibrium processes to continue. Energy passes through the system more evenly instead of surging through it violently. Gradients can persist without collapsing at once. Think of a living cell. Metabolic reactions inside it are constantly generating heat. If that heat were not managed, temperature would rise rapidly and disrupt the delicate chemistry on which life depends. But water, which makes up most of the cell's mass, absorbs that energy and redistributes it, keeping temperature within a narrow range, even while reactions continue. At a larger scale, the same principle holds. The ocean absorbs heat at the surface, currents carry it far away, and it is gradually redistributed over enormous distances. Energy enters, moves through, and leaves again, without destabilizing the whole system. Perhaps this is one of water's most important roles. It stabilizes instability itself. It does not freeze systems into rigidity, and it does not allow them to collapse into chaos. Instead, it keeps them in a dynamic balance, always operating, always responding, but not falling apart. Without this property, many processes would be driven toward one of two extremes, either too sluggish or too violent. Chemical reactions might overheat. Weather systems might become more extreme. Biological organization might become far harder to sustain. Water does not eliminate instability. It manages instability thermodynamically. It stands between incoming energy and the system's response, slowing transitions, stretching them out through time, allowing differences to exist without shattering at once. This happens differently at each scale, yet it all connects in one continuous thread. At the molecular level, hydrogen bonds absorb energy. At larger scales, bulk motion and convection carry heat away. At the planetary level, oceans and ice regulate energy exchange with space. The laws of thermodynamics remain intact. Entropy still increases, but the path entropy takes is shaped by water. Disorder does not erupt in jolts. It is guided through flows, step by step, layer by layer, and that is directly related to whether complexity can emerge at all. A complex system needs both stability and the capacity for change. Too rigid, and it cannot adapt. Too volatile, and it cannot hold any form long enough to persist. Water sits in that rare middle band. It allows continuous motion without pushing systems across catastrophic phase transitions. Prigogine emphasized that order can arise precisely under far from equilibrium conditions. Water is a medium in which that can happen gently. Energy flows through without tearing structure apart. Patterns form, dissolve, and return. Even very simple physical systems show this. Heat a shallow layer of water from below, and convection cells spontaneously appear, orderly patterns of motion emerging as the system finds a way to carry heat upward. They persist as long as the energy flow continues. Water does not resist the flow. It organizes itself around it. In more complex settings, the principle remains the same. Rivers carve stable channels as water continues to pass through them. Atmospheric circulation organizes into recurring wind patterns. Biological tissues maintain internal order while still exchanging energy with the environment. In all of these examples, the thermal properties of water sit near the core. This also helps explain why the temperature range suitable for life is relatively narrow and yet can still be maintained. Water's buffering capacity keeps temperature from shifting too quickly, giving chemical and biological processes time to respond, adjust, and continue. There is a quiet elegance in this. Water does not impose order. It simply softens extremes so that order has a chance to appear. It shields systems from abrupt fluctuations while still allowing them to respond to slower changes. In that sense, water is more like a regulator than a controller. It shapes the conditions under which complexity can endure without dictating what the outcome must be. From here, nature begins to look less like a collection of separate parts and more like a system of interactions, flows, and feedbacks. Water ties those scales together. Molecular interactions affect the stability of cells. Cellular processes affect ecosystems. Ecosystems in turn influence climate, and heat runs through the whole network. Water stands at the center of these flows not as a passive conduit, but as an agent quietly shaping how energy moves and how structures withstand time. What is striking is that this role comes with almost no drama. There are no sudden switches, no sharp thresholds that are easy to see. Water simply absorbs, redistributes, and releases energy, continuously and quietly, preserving balance while still allowing change to continue. Perhaps that is the most accurate way to put it. Water stabilizes instability not by stopping motion, but by giving motion somewhere to pass through. That is how systems can remain alive, dynamic, and enduring without ever having to fall into absolute stillness. And perhaps, more than any single anomaly, that capacity is the deepest explanation for why water lies beneath so much organized activity on this planet and beyond it. Water does not simply sit on a planet as an accidental covering. It enters into the very way that planet functions. Perhaps that is why, when science wanted to understand Earth more deeply, it gradually moved away from the habit of dividing it into separate pieces and studying each in isolation, and began instead to see it as an interconnected system. In the view that later came to be called Earth System Theory, the atmosphere, oceans, ice, land, and living organisms are no longer independent blocks. They are components linked by flows of energy and matter, and at the center of those flows, water appears as a crucial connector. It moves between reservoirs, changes phase, dissolves material, carries heat elsewhere, and forces processes that would otherwise remain separate to begin speaking to one another. One of the core ideas in this view is feedback. A process can alter the conditions around it, and those new conditions can then return to amplify or soften the original process. Water is present in some of Earth's strongest feedback loops. Temperature alone makes that clear. As the planet warms, more water evaporates into the atmosphere. Water vapor is itself a greenhouse gas, capable of absorbing infrared radiation and reducing the amount of heat that escapes into space. So the warming pushes itself a little further. At the same time, ice may melt, and ice reflects sunlight far better than liquid water does. As ice cover shrinks, the surface of the planet absorbs more energy, and the warming is reinforced yet again. In both cases, water stands at the center of positive feedback. But water does not only amplify, it also brings with it a kind of complexity that can restrain change. More evaporation can also mean more cloud formation. Clouds can reflect sunlight back into space and cool the surface, but they can also trap heat depending on their altitude and structure. So the net effect is not fixed. It varies with context. And that is perhaps the important point. Water is not a thermostat with a preset setting. It is more like a regulator whose effect emerges only through specific circumstances. James Lovelock contributed greatly to this way of thinking by emphasizing that a planet's conditions can remain within a life-supporting range over very long spans of time, even while being continuously disturbed from outside. The core of that approach, stripped of the misleading metaphors that sometimes cling to it, is not the idea of a planet intentionally caring for itself. It lies in feedback, interconnection, and long-term stability emerging from interaction. Water is an indispensable part of that interconnection. Volcanoes release gases into the atmosphere, including carbon dioxide, strengthening the greenhouse effect. But on geological timescales, water also participates in reducing that carbon through chemical weathering. Rainwater, made slightly acidic by dissolved carbon dioxide, reacts with silicate rocks at Earth's surface. Those reactions consume carbon dioxide, produce dissolved ions, and rivers then carry them to the sea. In the oceans, carbon can be locked away in sediments for millions of years. This is a slow mechanism, almost indifferent to short-term fluctuations, yet over the long run it is a very powerful stabilizing force on atmospheric composition. And throughout that entire cycle, water serves as the transport medium, linking atmosphere, land, and ocean. Without liquid water flowing across continents, chemical weathering would be far weaker, carbon regulation would decline, and climate would be much more prone to slipping toward extremes. The oceans themselves are also vast reservoirs of heat and carbon. They absorb roughly a quarter of the carbon dioxide entering the atmosphere from both natural sources and human activity. At the same time, they store far more heat than the atmosphere does, and in doing so they buffer changes in surface temperature. Ocean circulation then continues to redistribute that heat across the globe. Warm water moves poleward near the surface, cold water sinks and returns toward the equator in the deep ocean. This slow conveyor operates on the scale of centuries, smoothing thermal differences between regions. Once again, water is linking systems that would otherwise be thermally isolated. Ice contributes its own form of regulation as well. Glaciers and ice sheets respond very slowly to climate change, advancing and retreating over thousands of years. That slowness itself gives inertia to the climate system, making it harder to change course too abruptly. At the same time, ice affects sea level, ocean circulation, and the reflectivity of the planet's surface. What makes water's role so distinctive is that it is present across all timescales at once. Weather changes from day to day. Ocean circulation operates over centuries. Ice sheets evolve across millennia. Rock weathering unfolds over millions of years, and water participates in all of them. It is precisely this multi-scale presence that makes it such an effective planetary regulator. It does not maintain stability through one single rhythm, but by weaving fast and slow processes into the same network, allowing the planet to absorb disturbance without immediately falling apart. From a physico-chemical point of view, this requires no special assumption that the planet was somehow set up in advance. Everything follows outward from molecular properties already present. Phase changes, heat capacity, solvent behavior, transportability. Evaporation carries heat from the surface into the atmosphere. Condensation releases heat elsewhere. Dissolution brings ions from rock to sea. Freezing and melting redistribute energy and momentum. Each individual process follows relatively clear physical principles. What makes the difference is the way they are connected, and that is exactly what Earth system theory emphasizes. No single process sits in command of the planet. Regulation emerges from interaction. Water is effective not because it dominates, but because it connects. It is through that connecting role that a planet's behavior ceases to be the simple sum of separate parts and becomes instead a system responding to itself through countless overlapping feedback loops. Seen from that perspective, water is no longer just a substance present in rivers, clouds, or ice. It becomes the medium through which climate, geology, oceans, and life remain in contact with one another. And from here, that role becomes even clearer when Earth is placed alongside other planets. When Earth is placed beside other planets, the role of water becomes easier to see in a very direct way. Mars bears traces showing that liquid water was once present, but today it no longer has a stable hydrological cycle to keep those processes going. When liquid water is no longer stable at the surface, chemical weathering slows down. Carbon dioxide either accumulates or is lost to space without being effectively regulated, and temperature extremes become far harsher. Venus seems to have followed a different path, but it points to the same lesson. That planet may have lost its water very early on. Once the water disappeared, there was no longer any effective way to remove carbon dioxide from the atmosphere. The greenhouse effect intensified, and surface temperatures eventually climbed high enough to melt lead. Compared with those two extremes, Earth sits within a narrow middle range. Not because water itself is rare, but because on Earth, water is still active between the surface and the atmosphere. Of course, that does not amount to any permanent guarantee. Feedback loops can reverse, thresholds can be crossed, and regulatory mechanisms can fail. But over billions of years, water has helped preserve conditions sufficient for liquid water itself to continue existing. There is a closed loop here, but there is nothing mystical about it. Water regulates temperature, and that allows liquid water to remain. Liquid water enables weathering and circulation. Those processes help stabilize atmospheric composition. and that atmospheric composition, in turn, helps maintain temperature, a physical cycle, not a will. What matters is that this regulatory mechanism operates very slowly. It does not protect against sudden changes, nor does it respond on the timescales humans are used to feeling. It works through accumulation, delay, and gradual adjustment. Perhaps that is why the word stability is so often misunderstood. Stability does not mean stillness. It means resisting the tendency to slide into uncontrolled change over very long spans of time. And if Earth is viewed through that depth of time, the influence of water becomes much harder to deny. Over hundreds of millions of years, climate has changed dramatically. Ice ages have come and gone, continents have shifted, and oceans have opened and closed. And yet liquid water has remained persistently present at the surface through most of the planet's history. That persistence is not accidental. It is the accumulated result of countless interactions, with water itself standing in the middle as mediator. From the scale of hydrogen bonds to the scale of continents, the same substance keeps participating. The physical chemistry of water does not stop at the molecular level. It echoes upward, becoming flow, cycle, and feedback. In that sense, water is no longer merely one component of a planet. It is more like that planet's connective tissue, not a controller, not a designer, but a regulator whose influence emerges from motion, interaction, and time. The planet does not keep water standing still. Water moves through the planet, and in that movement it quietly helps determine the direction in which the planet will evolve. The relationship between water and life is often spoken of as though it were too obvious to deserve further thought. Life needs water, happens in water, and is largely made of water. But perhaps that very obviousness hides something deeper. Water does not instruct chemistry to become biology. It does not steer reactions toward life as though toward a predetermined destination. What it does is much quieter, but perhaps more important. It creates an environment in which chemistry can explore a very wide space of possibilities without immediately collapsing into dead ends. In that sense, water permits chemical diversification without directing it. And that distinction matters especially when we think about the origin of life. In many earlier conceptions, the story of life's origin was often told in a straight line. Simple molecules appear, combine into more complex ones, and eventually something living emerges. In such stories, water often appears as merely a convenient background for reactions to occur. Alexander Oparin argued against that simplification. From the early 20th century onward, he suggested that life did not appear as a neat leap, but through a long phase of chemical evolution, in which increasingly complex molecules accumulated and interacted in aqueous environments. In that view, water was no longer just the container. It was the medium that allowed complexity to persist long enough to begin mattering. Oparin emphasized that the early Earth was both chemically rich and physically dynamic. Energy moved through the system from sunlight, geothermal heat, and chemical gradients. Water was what connected those energy sources to reactive molecules, allowing them to mix, collide, and reorganize themselves. But the subtler point is that water does not favor any single outcome. In aqueous environments, countless reactions can occur at once. Some products are stable enough to remain, others vanish almost as soon as they appear. Many pathways open and are then abandoned. Water permits that kind of exploration by regulating energy, dissolving reactants, and carrying products elsewhere. That openness is what is essential. If chemistry were constrained too tightly, only a narrow band of reactions could persist. If it were too chaotic, complex molecules would be broken apart as quickly as they formed. Once again, water occupies that familiar middle ground, supportive enough for reactions to continue, yet buffered enough that extremes do not erase everything. One of the ways water does this is through solvation. When a molecule dissolves in water, it becomes surrounded by a shell of water molecules oriented around it. That shell stabilizes charged species and polar molecules, lowers energy barriers, and allows reactions that would be difficult in dry environments to become feasible. At the same time, water quietly discourages certain other arrangements. Non-polar molecules tend to cluster together, not because they attract one another especially strongly, but because water reorganizes itself to reduce the disruption they cause. This is an indirect influence, yet strong enough to shape molecular assembly without imposing any rigid template. The result is a chemical environment that is open-ended, not pre-directed, but not lawless either. Modern research in prebiotic chemistry has made that picture richer still. Experiments simulating conditions that may have existed on the early Earth show that, in water, many different reaction networks can be sustained. Sugars, amino acids, nucleotides, and simple lipids can all form under conditions considered plausible. None of those molecules, by itself, amounts to life, but taken together, they create a chemical landscape dense with possibility. And then research on hydrothermal vents adds another layer. Deep beneath the ocean, where seawater meets hot rock, very steep chemical gradients arise. In alkaline hydrothermal vents especially, natural proton gradients can form across mineral barriers, a setup that strongly echoes the very kind of gradient modern cells use to drive metabolism. In environments like these, water remains indispensable. It carries dissolved gases, moderates temperature, and also participates directly in reactions on mineral surfaces. More importantly, it allows those gradients to persist without immediately being flattened out. These are environments far from equilibrium, where energy continues to flow through the system, and in such places, water does not command chemistry to become life. It simply opens enough space, enough time, enough stability, and enough flexibility for chemistry to keep trying, keep failing, keep accumulating until something genuinely new begins to hold itself together. Even in settings that seem highly specific, water still refuses to force chemistry down a single path. In systems such as hydrothermal vents, matter is constantly passing through different states, and water is the medium that keeps those processes stable enough to persist. But that stability does not imply a predetermined outcome. A slight shift in temperature, a modest change in composition, or a different pattern of flow can send the resulting chemical mixture down another route. From this, a very important idea emerges: contingency. What happens depends not only on general laws, but also on particular histories, concrete conditions, local constraints, and even chance encounters. In such a system, there are always multiple possible futures. Water supports that contingency by keeping chemistry soft enough to keep trying. Precisely because it does not rigidly lock molecular arrangements into place, water allows many pathways to coexist. Molecules can assemble, come apart, and then reassemble in different ways. Structures can appear temporarily, break apart, and then reappear in a new form. This is very different from environments in which chemistry is constrained too tightly, such as on solid surfaces or in media that are too viscous. There, once a shape has formed, it may be held in place, slowing exploration considerably. In water, exploration continues, and that is exactly why life should not be seen as an inevitable endpoint. On the contrary, the openness of chemistry in water suggests that life was only one among many possibilities that might have occurred. Water opens opportunity. It does not write destiny. When biological systems began to appear, water's role did not disappear, but its tone changed. It still allowed diversity, still maintained space for many possibilities, but now biology began to introduce its own specificity. Proteins folded into highly precise shapes. Nucleic acids stored information. Membranes formed controlled boundaries. All of those structures depend on the properties of water, yet at the same time they impose constraints on chemistry that the aqueous environment itself does not impose. Here, too, water remains more of a partner than a commander. The hydrophobic effect may drive protein folding by hiding nonpolar regions from water, but the final structure of a protein is not encoded by water. It is determined by the amino acid sequence itself. Likewise, enzyme reactions need water to stabilize charges and support proton transfer. but the specificity of the reaction comes from the shape of the enzyme, not from the water. That is a distinction very easily blurred, because water is everywhere in life. Cells are mostly water. Metabolism occurs in aqueous solution. Signals propagate through ions moving in water. But life is not simply chemistry occurring inside a liquid. It is chemistry that has learned to make use of the permissiveness of water while also constructing its own limits and rules. In that sense, the transition from prebiotic chemistry to biology is a selective narrowing of possibility. Many reaction pathways are closed off, some others are reinforced. Feedback mechanisms begin to appear that retain successful configurations. Water remains the environment in which everything happens, but it is no longer the party deciding the rules of the game. It provides the stage and the conditions, not the script. Seeing it this way helps avoid a very common misunderstanding. Water does not, by itself, make life appear. But life did not arise in spite of water, either. What happened is that life emerged within a chemical environment flexible enough to explore complexity, yet stable enough not to destroy it too soon. That kind of balance is rare. On planets without liquid water, chemistry is often either frozen in place or driven too violently by energy. On planets where water exists only briefly, reaction networks may not last long enough to evolve. Earth's long-lived oceans created a very different kind of continuity. They gave chemical experiments hundreds of millions of years to unfold without interruption, allowing rare combinations time to accumulate, encounter one another, and test whether they could go further. Even after biological systems appeared, the openness that had made their emergence possible did not vanish entirely. To this day, water still permits variation, mutation, and adaptation. It stabilizes reactions without imposing outcomes. It supports change without forcing change to move in any single direction. Perhaps this is water's quietest contribution to life. It does not choose the winners. It merely keeps the game going. From prebiotic mixtures to living cells, water has always allowed chemistry to continue exploring, refining, and specializing without ever fully closing the door of possibility. And in that quiet permission, the foundations of biological complexity began to be laid. This becomes especially clear when one looks at proteins. In textbooks, proteins are often drawn as tidy ribbons folded into precise shapes, almost as if they had been designed. That image makes it easy to imagine that a protein simply snaps into its final structure and then remains there. But reality is far more dynamic. A protein is only a chain of amino acids, sometimes hundreds of units long, connected in a defined sequence. That chain does not, by itself, carry any obvious final shape. It can bend, twist, and fluctuate in countless ways. If everything were truly left entirely to chance, the number of possible configurations would be unimaginably vast. Trying them all might take longer than the age of the universe. And yet in cells, many proteins still fold reliably within seconds. It was precisely this apparent contradiction that Cyrus Leventhal brought into focus in the 1950s. But even earlier than that, Walter Kaufmann had recognized a deeper layer of the question, centered on the hydrophobic effect. At first, the phenomenon seems almost too familiar. Oil and water separate. Non-polar regions tend to cluster together. But what Kaufmann noticed was that the driving force behind this process might not lie in any especially strong attraction between non-polar groups. The paradox is that the true motive seems to come from water itself. The non-polar side chains of amino acids do not pull each other together through any remarkable force. What actually happens is that the surrounding water molecules are forced into a more constrained arrangement, and in doing so they lose some of their freedom to maintain their own hydrogen bond network. That state is energetically costly. When non-polar groups cluster together and hide from water, the surrounding liquid is freed to organize itself more comfortably, and the entire system becomes more stable. So protein folding is not simply a story of parts of the protein attracting one another and closing in. It is also a story of water pushing some arrangements away and making others more favorable. This is a very characteristic kind of indirect causality. The solvent shapes the outcome without dictating it in advance. Once that is recognized, the way protein folding is described also changes. Instead of imagining a single path leading straight to the final structure, science began to think in terms of an energy landscape. All the configurations a protein might adopt are pictured as a rugged terrain, where each state corresponds to its own energy level. High-energy states are unstable and only rarely occupied. Low-energy states are more stable and easier to reach. For proteins in water, that landscape resembles a rough funnel. Many configurations exist high above, and as folding proceeds, the protein chain gradually moves downward, guided at once by interactions with itself and with the surrounding water. Even once a protein has begun moving downhill along its energy landscape, that path is never truly smooth. There are local hollows where the chain can become trapped, pause, or even misfold, but the overall tendency still leans toward a more stable form. What is striking is that the entire landscape is not determined by the protein alone. It is carved by the surrounding water. Change the solvent, and the landscape changes with it. A protein may fold very easily in water yet fail to fold at all in another liquid, or collapse into a completely different shape. So the problem of protein folding was never something that could be separated from the environment in which it occurs. That is also why attempts to understand proteins in isolation so often go astray. In a vacuum, proteins behave very differently. Charged groups act on one another too strongly, and structures can collapse or distort because the delicate balance normally provided by water is gone. Water screens, charges, moderates attractions, and makes the exposure of non-polar surfaces energetically unfavorable. In other words, it sets up a system of quiet constraints that guides the folding process without controlling it step by step. That guidance is extremely subtle. No single hydrogen bond between water and protein is enough to determine the final structure, but millions of fleeting interactions, taken together, are enough to tilt the probabilities towards certain configurations. And even once folded, proteins do not become rigid objects. They still breathe. Side chains vibrate, rotate, and shift slightly. Even the most stable structures continue to fluctuate. Those motions are not meaningless noise. They are what make function possible. Enzymes need flexibility to embrace a substrate and then release a product. Structural proteins must withstand stress without breaking. Signaling proteins often have to alternate between different shapes depending on their surroundings. Water accompanies all of this motion. It fills cavities, stabilizes transient charges, and absorbs energy from conformational changes. Without water, the very fragile balance between stability and flexibility would be lost. So protein folding is not a search for one perfect final shape. It is the arrival at a family of shapes stable enough to persist, yet soft enough to function. Water supports exactly that balance. The hydrophobic effect tends to bury non-polar regions inside, but not lock them away forever. Hydrogen bonding with water stabilizes polar regions while still allowing them to rearrange. Electrostatic screening prevents charge from dominating the entire structure. Together, those influences create a system that is robust without becoming brittle. And it is precisely this kind of resilient softness that underlies biological complexity. Living systems depend on countless proteins interacting in a crowded, noisy environment. Errors still occur, temperature still shifts, concentrations still fluctuate, conditions still drift slightly, and yet biological function continues. Here, water plays a central role in that resilience. It buffers interactions, absorbs disturbances, and allows the system to test small variations without collapsing catastrophically. Even misfolding, often treated simply as an error, reveals this same flexibility. Proteins can fall into alternative structures under stress. Some of those states are reversible. Some are recognized and managed by the machinery of the cell. The system does not merely endure, it adapts. From a purely chemical point of view, none of this is truly obvious. A long amino acid chain ought to be extraordinarily hard to predict. The fact that it is not entirely so is the result of a kind of indirect causality, in which water constantly stands in the middle as mediator. This perspective also helps explain why protein design is so difficult. Knowing the sequence alone is not enough. The environment matters just as much. Solvent, temperature, ionic strength. Crowding all of it reshapes the energy landscape. Biological specificity, therefore, does not arise from a rigid command, but from constraints and probabilistic biases. Water excludes what is unfavorable, increases the chances of what is favorable, and still leaves room for variation. That is a very powerful recipe for complexity. At a deeper level, protein folding seems to illustrate a broader principle of biology. Order does not necessarily appear because the components actively impose it, but because the environment makes some arrangements easier than others. Water does not tell a protein what shape to fold into. It simply makes certain folds more energetically comfortable than others. As systems grow larger, the significance of that difference becomes even clearer. Networks of proteins interact, assemble, and come apart. Pathways overlap, feedback loops emerge, and the stability of the whole system is supported by countless tiny interactions, most of which bear the fingerprints of water. In that sense, water is not merely the medium of life. It is part of the very mechanism by which biological order appears and persists. Protein folding is one of the clearest examples of that partnership. A simple chain becomes a functional machine, not because it is directly instructed, but because it moves across a landscape shaped by the solvent that is always present around it. And then, when one goes deeper still into the cell, the story becomes subtler again. Water is everywhere there, but it is no longer uniform. A cell is not a cup filled with homogeneous liquid. It is a crowded, structured environment, dense with proteins, membranes, nucleic acids, and molecular machines, all operating in close quarters. Even though water still makes up most of the mass, much of it is not free in the same way as water in an ordinary glass. It is confined, influenced by nearby surfaces, or altered by the surrounding environment itself. From that arises the next question. Does water inside the cell still behave like ordinary liquid water? The most careful answer is partly yes, partly uncertain, and it takes a great deal of care to say more without going too far. Some features of intracellular water are fairly well established. Other claims remain controversial. The problem is not that the question is strange, but that it is very hard to measure water at exactly that scale without disturbing it in the process. One of the most prominent ideas here is associated with Gerald Pollack and the concept of exclusion zone water. According to that proposal, water next to certain hydrophilic surfaces can form a region that pushes dissolved substances away, carries different electrical properties, and may be more ordered than bulk water. Some experiments do indeed show that near certain kinds of surfaces, especially charged or polar ones, dissolved particles are excluded over distances larger than one would ordinarily expect, sometimes extending tens or even hundreds of micrometers under particular conditions. That is a range far beyond the molecular scale interfacial layer usually considered in surface chemistry. What matters is this: the observation that water near surfaces can behave differently from water farther away is real, and in some experimental setups, reproducible. Water near membranes, proteins, or mineral surfaces often has altered orientation, slower motion, and a modified hydrogen bond pattern. But the debate begins at the stage of interpretation. One reading of the results is that this points to a distinct phase of water, fundamentally different from ordinary liquid water. And that is exactly where many physical chemists and biophysicists begin to slow down and keep their distance. They agree on the narrower point. Water near interfaces really can be more structured, can have properties different from bulk water. Hydrogen bonding can become more ordered, motion can be more constrained, and electrical behavior can also differ. But how far those effects extend, how stable they remain under physiological conditions, and how important they are inside living cells, those are still open questions. A cell is far too dynamic a place for any structure to be easily assumed stationary. Proteins move, membranes bend, ions flow constantly, water is displaced, reorganized, and exchanged without end. If there are regions of more organized water, they must exist within that very instability. So experimental ambiguity is almost unavoidable. The tools used to measure water structure, such as nuclear magnetic resonance, infrared spectroscopy, or neutron scattering, usually give us averages, pooled across very many molecules and very many timescales. And precisely because water is both so familiar and so difficult to grasp at this level, the question of water inside the cell still hangs at the boundary between what is securely known and what must still be held with caution. The deeper science goes into water, the more it runs into a difficult paradox. We can understand it only through measurement, yet water's behavior keeps exceeding what measurement can fully capture. Inside the cell, that paradox becomes especially clear. Today's techniques can detect changes in how mobile water is, in the patterns of its bonding, and in the way it responds near surfaces. But there is still a long distance from data to interpretation, because data do not speak for themselves. They need models, and sometimes different models can explain the same signal equally well. A layer of water moving more slowly near a surface may be read as evidence of a specially ordered region, but it could also simply be the consequence of molecular crowding or of temporary interactions with nearby structures. Distinguishing among those possibilities is very difficult. That is not a failure of experiment. It is a limit imposed by the scale itself. Inside the cell, water almost never has a chance to become the kind of bulk water one finds in a laboratory cup. Within just a few nanometers, it encounters another surface, a membrane, a protein, a nucleic acid, some molecular machine. In that sense, intracellular water is almost always interfacial water, so the fact that it carries some degree of structure near surfaces is not surprising at all. The real question is not whether that exists, but how strong it is, how far it extends, and what it means for cellular function. This is exactly where a very sober distinction becomes necessary: the difference between structural influence and functional significance. Even if water near an interface truly is somewhat more ordered, the important question is still not automatically answered. Does that ordering actively govern processes like protein folding, enzyme activity, or ion transport? Or is it simply part of the background condition that cells have long since learned to live with? There are very attractive hypotheses that lean toward the first possibility, but the evidence is not yet decisive. In many cases, what is observed can still be explained through more familiar concepts: ordinary electrostatics, hydration layers, or molecular crowding without invoking a new phase of water. That does not make the question any less interesting. It simply forces precision to come before the appeal of large explanations. Part of the reason this subject keeps attracting attention is that it breaks the tidy picture textbooks often leave behind. Cellular chemistry does not occur in a dilute, uniform, gentle solution. The cell is dense, crowded, full of obstacles. The effective concentration of macromolecules is high. The amount of truly free water is smaller than intuition suggests. All of that crowding alters reaction rates, diffusion, and the way molecules interact. Water stands in the middle of all those changes. Near membranes, it rotates in response to polar head groups. Near proteins, it forms hydration layers that help preserve structure and support motion. Near nucleic acids, it softens the charges running along the molecular backbone. Effects like these rest on fairly solid experimental ground. What begins to grow more fragile is the leap from such local order to claims about large-scale, long-lived organized regions strong enough to govern the behavior of the whole cell. Most of the evidence at present points toward a more cautious picture. Those structured regions of water are local, short-lived, and extremely sensitive to conditions. Change the temperature, ionic strength, or molecular composition even slightly, and the water changes too. That very sensitivity makes generalization difficult, and it also helps explain why different laboratories sometimes do not see exactly the same thing. A small difference in surface treatment, sample purity, or measurement technique can make an exclusion zone appear very clearly in one place, yet shrink or even disappear in another. So caution here is not avoidance. It is part of scientific precision. And for that reason, the strongest current position is probably this: water inside cells is heterogeneous. Its properties vary with distance from surfaces, with local charge distribution, and with the degree of molecular crowding. Some degree of structuring near interfaces is real and measurable, but claims about large-scale, long-lived alternative phases have not yet been demonstrated convincingly. That careful distinction matters not only because it keeps an argument from outrunning the evidence, it also helps science ask the right question. Because if even inside the cell, one of the most thoroughly studied environments, water still proves this difficult to describe, then how trustworthy are the methods used to study water in general? That question pushes the issue beyond biology and into the limits of measurement itself. Trying to measure water is, at some level, like trying to photograph a crowd while everyone is constantly changing places. By the time the image is captured, the real moment has already vanished. At the molecular level, water is never still. Hydrogen bonds form and break on extremely short timescales. Molecules rotate, vibrate, and slip past one another. Local structures appear and disappear faster than most instruments can follow. So any attempt to observe water risks flattening the very motion that makes it such a difficult object to grasp. For most of the history of science, that limit was almost invisible, simply because what people measured were mostly static quantities. Density, boiling point, heat capacity, compressibility, all of them are highly reliable numbers, but they are averages, and averages conceal dynamics. Only as understanding advanced did researchers gradually realize that what makes water special does not lie in a motionless structure, but in motion itself. From that point on, the emphasis changed. It was no longer only a matter of where molecules are in space, but of how long they remain there, when they leave, and how they are replaced. Time resolution began to matter just as much as spatial resolution. Knowing where an atom is can be useful. Knowing how long it will remain there is sometimes what really matters. Many traditional techniques are excellent at resolving space, but tend to blur time. X-ray diffraction is a classic example. It is superb at reading the order of crystals. But liquid water does not crystallize. And even when there are patches of short-range order, they fluctuate too quickly to remain fixed, long enough for a sharp image. What one gets instead is a time-averaged picture, smoothed over countless rearrangements. Spectroscopic methods offer another route. From the way water absorbs or emits at certain frequencies, one can infer something about motion and bonding. Infrared spectroscopy, Raman spectroscopy, nuclear magnetic resonance, all are extremely powerful. But even here, the problem returns to the same place. A signal that looks stable may simply be the result of fluctuations happening too quickly for the measurement to resolve. Without understanding the timescale properly, it becomes very easy to mistake motion for structure. The importance of time only truly became clear once ultra-fast techniques appeared. Ahmed Zewail's work in the late 20th century helped define an entirely new field, femtochemistry. With extremely short laser pulses, chemical reactions could finally begin to be seen while they were actually happening, on femtosecond timescales so brief that atoms themselves seemed to be exposed in motion. Bonds were no longer merely something inferred afterward. They could be followed as they formed and broke. Fleeting states that had once existed only on paper began to enter the measurable world. When tools like these were applied to water, what emerged was not a liquid holding some stable preferred geometry, but a world in continual reorganization. Hydrogen bonds stretch and collapse on extremely short timescales. Vibrational energy spreads through the network almost immediately. Local structures flash into being and vanish. All of it confirmed something theory had already long suggested. The properties of water arise from motion, not from some quiet, static scheme underneath. But even here, the limit does not disappear. To observe a system, one must touch it in some way. A laser pulse, however brief, still delivers energy into the sample, and so the measurement itself enters the story as an intervention. An experiment can be designed more carefully to minimize that effect, but it cannot remove it completely. Perhaps this is one of water's most characteristic features. The more closely we look, the more we find that the thing we want to grasp and the very act of grasping it cannot be cleanly separated. And that is why the science of water has always demanded more than better instruments. It demands better questions, clearer boundaries between what is known, what is inferred, and what must still remain open. The harder science tries to see water clearly, the more it is forced to confront a limit that is difficult to avoid. The observer is not outside the process. With water, that limit becomes especially sharp because it is a system that responds too quickly, too sensitively. A tiny disturbance, a little heat, an electric field, a nearby surface, a confined space, is enough to shift the rhythm of the hydrogen bond network. So in the very moment we introduce a measurement, we have already begun to alter the thing we want to see. That does not make observation meaningless, but it does force interpretation to become far less arrogant. Each technique sees only one face of water. Neutron scattering is especially sensitive to the positions of hydrogen, but it folds everything into a time average. Infrared spectroscopy captures vibrational dynamics, yet getting from signal to structure requires crossing a bridge of delicate models. Nuclear magnetic resonance reveals something about mobility and environment, but often lacks sharp spatial resolution. No method provides the whole picture. Combining many methods improves matters, but the picture does not become simple for that reason. Data from different observational windows still have to be fitted together. Gaps must be bridged by theory, and it is precisely at those joints that assumptions begin to slip in. From this point on, water begins to appear not only as an experimental problem, but as a problem of modeling. Experiment produces signals, but a signal is not a molecular description. It has to be translated, and translation always passes through a theoretical framework, a computational model, a set of decisions about what is preserved and what is blurred away. If the model is incomplete, or tilted in some direction, then the interpretation tilts with it. This has been a persistent difficulty in the science of water. One model may reproduce bulk properties very well but fail at interfaces. Another may describe hydrogen bonding beautifully yet lose track of long-range correlations. Some models emphasize electronic structure, while others accept less detail in exchange for speed. No choice covers everything. Time resolution makes the matter even subtler. A model that fits average behavior extremely well may still miss fleeting states that matter for a particular process. On the other hand, a model that tracks ultra-fast dynamics closely often becomes too expensive to scale up to large systems. The result is that our understanding of water has the character of a patchwork quilt. Each piece has value, but no piece is enough to stand in for the whole. This is not a sign of carelessness. Water is one of the most intensely studied substances in science. That only makes it clearer that the difficulty here comes from the nature of the object itself, a system whose decisive properties are collective, always moving, and extraordinarily sensitive. Even the word structure itself begins to lose its familiar clarity. If a hydrogen bond exists for only a tiny fraction of a picosecond, does it still deserve to be called a meaningful entity? If a network changes its membership continuously, is it really a network at all? These are not word games. How one answers such questions directly shapes how experimental results are read, and the observer's limit does not lie only in the instrument. It also lies in human intuition itself. We are very inclined to imagine water as a static structure, with motion as mere noise laid on top. But with water, perhaps the thought must be reversed. Motion is the structure. When a scientist speaks of the structure of liquid water, what they usually mean is a statistical tendency, not a fixed object. Peaks in a distribution function, correlation lengths, average orientations, these are tendencies, not things. Unless that is made explicit, water can easily seem full of contradictions. One experiment sees order, another sees disorder, and both can still be right within their own windows of time and space. Perhaps this is what water forces science to learn. No single snapshot is enough to tell the whole story. Time resolution determines which rhythm of the system we can see. Spatial resolution determines how local the visible phenomenon is, and the observer's own impact determines what survives the measurement. These limits are not unique to water, but water amplifies them because its behavior is both so fast and so cooperative. At the molecular scale, there is almost no stationary frame of reference to hold on to. Everything is moving relative to everything else. Every technical improvement, faster ultrafast spectroscopy, finer scattering methods, longer and more accurate simulations reveals another layer of detail. But the target does not become easier to understand as a result. It simply becomes richer in detail, and therefore harder to confine within a single frame. This has very practical consequences for the way science builds confidence in models. A model is always an approximation. With water, the question is not whether a model is absolutely right, but which part of reality it captures well and which part it smooths away. Recognizing that helps guard against false certainty. It pulls attention back toward uncertainty, rather than creating the illusion that a final description has already been completed. And it is exactly here, when experiments become sharper yet water still refuses to sit still for a final portrait, that science turns in another direction. If water cannot be held still long enough to be measured cleanly, perhaps it can be reconstructed inside a computer. That idea has guided decades of molecular modeling. If every atom, every molecule, every interaction in water could be calculated step by step, then perhaps its behavior would gradually reveal itself. The basis of most such efforts is molecular dynamics. In this approach, atoms are treated as particles moving under the forces between them. Their positions and velocities are updated continuously in extremely small time steps, so that the whole system evolves together. But everything depends almost entirely on how those forces are written down. And that is where the concept of a force field enters. A force field determines how atoms attract or repel one another, how bonds stretch or bend, how strongly charges interact. For water, that means choosing parameters for bond lengths, bond angles, partial charges, and the way hydrogen bonding itself is represented. The important point is this: these force fields do not fall directly out of nature's deepest principles. They are constructed. Most are empirical or semi-empirical. Their parameters are tuned so that the model reproduces certain known properties: density, diffusion coefficient, heat capacity, dielectric constant. When a model performs well on those, it is regarded as successful. But that success is always selective. A force field optimized for bulk properties may perform poorly at interfaces. A model that works beautifully at room temperature may drift at high pressure. Some models reproduce structure well but get dynamics wrong. Others do the reverse. This is not a technical flaw. It reflects an uncomfortable but fundamental truth. No finite set of parameters can fully capture a system as complex and sensitive as water. For that reason, different force fields often disagree with one another. They may produce different hydrogen bond lifetimes, different degrees of local order, different responses to temperature or pressure. All of them may sound reasonable. All of them may fit part of the experimental data, yet they still do not converge on a single picture. From that come the long-running debates in the field. One of the major dividing lines has been between empirical modeling and approaches that try to move closer to quantum mechanics. The latter are often grouped under the name ab initio. Instead of imposing interactions through pre-tuned parameters, they try to calculate them from first principles. Here, density functional theory plays a central role. In principle, it allows interactions to be inferred from the very distribution of electrons in the system. But even that route does not escape approximation. The exact mathematical form of electron interaction is not fully known, so approximate functionals still have to be used. Each functional emphasizes a different side of behavior. Some handle hydrogen bonding better, others fall short on dispersion forces. No choice is right in every case. And beyond that, ab initio simulations are so computationally expensive that the ability to follow large systems or long times quickly becomes another limiting factor. So even when science brings water into the computer, the story does not become simpler. It merely shifts from a difficulty of measurement to a difficulty of description, and once again reminds us that, with water, moving closer to the details usually also means discovering that even more layers of uncertainty still lie ahead. Even after bringing water into the computer, the problem does not disappear at all. It merely changes form. Simulating large volumes of water over long periods of time remains extremely difficult, so every existing method has to accept trade-offs. On one side of the balance is scale. Empirical force fields can track millions of molecules and let the system run for a long time, but the price is that they depend on assumptions already embedded in their parameter sets. On the other side is microscopic fidelity. Ab initio approaches come closer to the true electronic effects, but they have to shrink the system and shorten the simulated time span. Neither side is in a position to claim to be the final voice. What makes this even subtler is that models are usually judged by how well they reproduce quantities observed in experiment. But experiment itself, as we have seen, is not a transparent mirror. It has already passed through averaging, modeling, and interpretation. So a model may fit one dataset extremely well and still conflict with another. And from that comes a point worth pausing over. Fitting the data does not mean being right about the mechanism. Two completely different models can reproduce the same average behavior, only each reaches it through a different internal logic. One model may hold hydrogen bonds more rigidly than reality does. Another may allow more fluctuation but compensate through other interactions. If the underlying motion cannot be seen directly, it is very difficult to say which description lies closer to the real world. It is exactly here that assumptions begin to accumulate quietly. Every model must decide what to keep and what to leave out. Should hydrogen atoms be represented explicitly or absorbed into an average? Should charge polarization be allowed to respond to the environment or be fixed in place? Should the quantum effects of nuclear motion be included or approximated with classical mechanics? None of these choices is neutral. Each reflects a judgment about what matters, what is feasible, and at what scale detail is still truly necessary. When different research groups make different judgments, disagreement is only natural. That does not show the field is in disarray. It shows that water lies right at the edge of what current modeling tools can bear. Liquid water is not like a rigid solid with a stable structure, nor like a dilute gas where interactions are fleeting and then vanish. It lives in between. Interactions are strong enough to matter, yet fragile enough to keep fluctuating. Its collective behavior is woven from countless small effects, and capturing that requires a very difficult balance between detail and computational tractability. As computational power grows, models become more sophisticated as well. Polarizable force fields allow charge to respond to the environment instead of remaining fixed. Machine-learned potentials attempt to learn patterns of interaction from enormous datasets. Hybrid methods try to connect quantum-level description with classical-level description, but each advance brings new questions. Adding polarization improves the description of dielectric behavior, but at the cost of greater computational expense and a more complex parameter set. Machine-learned potentials can reproduce beautifully what they were trained on, yet outside familiar territory they may drift very far. Hybrid methods require an extremely careful stitching together of levels of description that speak in fundamentally different languages. No path escapes trade-offs. From there, the question of modeling water begins to slide into a more philosophical register. What, after all, is a model? Should it be a close replica of reality, or merely a tool good enough to reproduce a few important behaviors? If a model predicts observable quantities correctly but its internal picture seems artificial, should we accept it? Or should physical plausibility be valued above numerical fit? With water, there is no single answer, and perhaps there does not need to be. In practice, models of water often function as hypotheses. They propose a way the system might behave, remain constrained by known principles and experimental data, and then allow experiment to test the consequences. Seen in that way, disagreement is no longer a malfunction. It becomes a productive part of knowledge. In that sense, modeling water is not a journey toward one final completed portrait. It is more like mapping a space of possibilities. Each model illuminates one mechanism and blurs another. Only together do they begin to form a patchwork understanding. This also explains why debate has remained so persistent after decades of work. Water refuses to collapse into a single framework. Its behavior stretches from the quantum domain into the classical one, changes with context and scale, and resists every attempt to compress it into a minimal rule set. Models of water merely reflect that resistance. They contain assumptions because they cannot do otherwise. They simplify because they cannot avoid simplifying. They disagree because each style of simplification touches a different part of the truth. Recognizing that does not weaken science. On the contrary, it clarifies the real limits and strengths of science. A model is not a mirror, it is a lens. A lens brings some details into focus and blurs others. With a substance as complex as water, no lens is enough to see everything. This realization calls for a very necessary kind of humility, but it also opens a different kind of creativity. By comparing lenses, seeing where they succeed and where they fail, scientists learn not only more about water, but also more about the limits of representation itself. They learn how collective behavior breaks reductionist thinking. They learn where intuition is no longer trustworthy. And water, in that way, becomes almost an exemplary case of how scientific knowledge is built, not as a finished image, but as an evolving sequence of approximations, each anchored in evidence, each always open to revision. Even within physics itself, liquid water occupies a very strange position. It is everywhere, immensely useful, studied in extraordinary detail. Yet in condensed matter physics, it still remains one of the clearest examples of a problem that refuses to close. Solids are easier in some respects, because their atoms hold fixed positions and merely vibrate around them. Gases are also easier in their own way, because particles interact weakly and briefly. Those two extremes allow rather clean theoretical descriptions. Liquids, by contrast, lie in between, borrowing from both sides without fully belonging to either. Their atoms are close together, as in solids, but constantly exchanging places as in gases. Their interactions are strong enough that they cannot be ignored, yet fleeting enough that they cannot be locked into a simple scheme. This intermediate nature already makes liquids in general difficult to generalize. And among them, water stands out as a particularly stubborn case. Condensed matter physics has built powerful theories for crystals, magnets, superconductors, and other phase transitions, often grounded in concepts such as symmetry, order parameters, and long-lived structures. But liquid water does not naturally carry those things in any stable form. Its order is only local and short-lived. Its correlations are always fluctuating. Its structure is statistical rather than geometric. Philip Ball has devoted much effort to synthesizing and interpreting this very tension, not as an act of popular mystification, but as a deeply real scientific fact. The difficulty of water is not exaggerated. It really does sit at the edge of what current theoretical frameworks handle smoothly. Part of the reason is that liquids in general still lack a unified theory in the sense that solids and gases possess one. For solids, lattice models provide a common language. For gases, kinetic statistical theory does something similar. But for liquids, there is no equivalent universal framework. Each substance often has to be approached through its own approximations, matched to its particular interactions. Water makes the problem harder still because it gathers too many competing tendencies into one system. Hydrogen bonding pulls the system toward local order. Thermal motion tears that order apart. Electrostatic interactions reach farther. Molecular geometry imposes directional constraints, yet no tendency is strong enough to seize complete control. The whole system keeps itself poised at the edge between structure and disorder, and it is precisely at that edge that intermediate states appear. At any moment in liquid water, there are regions that remind us of ice. Elsewhere, it looks more like a disordered liquid. Between those two ends lies an entire continuum of transitional configurations, with no sharp boundary separating them. Water simply moves through all of them. These intermediate states are not incidental details. They touch directly on measurable quantities. The density anomaly, compressibility, heat capacity, response to pressure, all depend on how the population of local structures shifts as conditions change. And this is also where everything becomes difficult to describe rigorously. In a crystal, a phase transition comes with a clear change of symmetry. In a gas, change is smoother and more predictable. But in liquid water, the transitions are blurred. Structural motifs do not simply switch on or off. They fade, reappear, and change in probability. So even the most basic question begins to wobble. What is the proper degree of freedom for describing water? Should one begin from individual molecules, from the hydrogen bond network, from clusters, from density fluctuations? Each description captures something real, but none captures everything. And perhaps that is exactly where water holds its special place in science. Not as an incomprehensible mystery, but as a system so familiar that it seems as though it ought to be simple. Yet the longer one looks, the more it forces the admission that understanding sometimes does not arrive through a single answer, but through learning how to live with multiple partly correct descriptions, overlapping, correcting one another, and together moving closer to what is actually happening. There is something about liquid water that I have always found almost paradoxical. We use it as the standard liquid against which other substances are compared. And yet it is precisely this substance that refuses to remain still within any stable explanation. If this were merely some rare material, that uncertainty might be easier to accept. But water is not obscure at all. It is too familiar, too foundational, and that is exactly what sharpens the problem. In condensed matter physics, the usual aim is to find minimal models, concise descriptions still capable of capturing the essential behavior. With water, that path repeatedly stalls. Remove hydrogen bonding, and the anomalies disappear. Remove electrostatic interactions, and the structure falls apart. Remove motion from the picture, and the liquid freezes into rigidity. What remains is no longer water, and so water forces us to confront an uncomfortable but serious possibility. Perhaps not every system can be reduced to a single, elegant, final description. Some systems may require layers of explanation stacked on top of one another, each valid only within its own domain. Liquid water seems to be exactly such a system. The interactions that compose it, taken one by one, are not mysterious at all. But once they enter the collective, they generate behavior so subtle that no single interaction is sufficient to explain it, and no single scale truly takes command. That is why water sits at the edge of current theory, not in the sense of some dramatic mystery, but as a problem lying right at the boundary of our conceptual reach. What experiments reveal only makes the picture more layered. Scattering shows short-range order, yet no repeating periodic pattern. Spectroscopy records distinct vibrational modes, yet they are strongly broadened by motion. Thermodynamic measurements show very clear anomalies, yet they do not point to a single microscopic origin. As a result, several interpretations continue to coexist. Some models see in water the trace of local tetrahedral order inherited from ice. Others focus more on density fluctuations, suggestive of the vicinity of a critical point. Some hypotheses propose that at low temperatures, water contains two liquid-like states shifting back and forth between one another. Others argue that no such distinction is necessary. What matters is that each view has evidence on its side, and each is also challenged by other data. The persistence of this disagreement does not mean stagnation. At the scientific frontier, that is often the normal rhythm. No single experiment hands us the decisive picture. No single simulation is powerful enough to end the debate. Each advance merely adds detail, tightens the constraints, and then opens new questions. So to say that water remains an unsolved problem does not mean that humans understand it poorly in practice. Engineers still use it reliably. Biology still depends on it. Climate models still incorporate its behavior with significant success. What remains open lies deeper than that. Why water's anomalies cluster together the way they do, how local order propagates, and whether all of that behavior can be unified within some broader theoretical framework for liquids. Perhaps the root of this resistance lies in the nature of complexity itself. Many scientific problems over time gradually converge. Better tools, more data, narrower uncertainty, competing theories falling away, consensus emerging. Water has not followed that path in the way people expected. This is a system made of countless interacting components, where collective behavior cannot be predicted simply by dissecting the parts in isolation. Each water molecule obeys simple physical laws. The interaction between each pair of molecules has also been described fairly clearly. But when countless numbers of them interact together, the result is no longer a simple sum of those pairwise interactions. That is a classic sign of nonlinearity. In a linear system, knowing the parts is enough. Double the input, and the output doubles as well. With water, context decides everything. Near the freezing point, a small change in temperature can make water expand instead of contract. A very slight change in pressure can bring forth new structural motifs. A small difference in composition can be enough to alter behavior on a much larger scale. What seems simple at the molecular level suddenly becomes difficult to foresee at the collective level. This is where the perspective of complexity science begins to become useful. Murray Gell-Mann explored such phenomena through the lens of complex adaptive systems. Water, of course, does not adapt in the biological sense, but its hydrogen bond network is continuously responding to local conditions. Bonds form where they are energetically favorable and break where they are no longer so. Patterns self-adjust, the system reorganizes itself, and no central control is required. Seen this way, the reason reductionism begins to lose its footing also becomes clearer. Reductionism has delivered great victories for science, but with water, knowing everything about one isolated molecule is still not enough to understand liquid water. Knowing everything about a pair of molecules is still not enough to understand the network. And even once we understand quite a lot about local clusters, large-scale behavior still is not fully determined. At every layer, new interactions enter the story. That does not make reductionism a mistake. It only shows that reductionism, by itself, is not enough. Water demands a complementary approach, one focused on collective behavior and interaction across many scales. All it takes is asking one seemingly simple question to see this. At what scale does water truly become water? Not at the level of individual molecules, because in isolation they behave very differently. Not at the level of hydrogen bond pairs, because those are too fleeting. Not quite at the level of clusters either, because they constantly rearrange. The properties that make water recognizably itself do not appear suddenly at some privileged threshold. They emerge gradually across a continuum. That is one of the strangest things about water. Many other physical systems have a clear anchoring level. Crystals have their lattice. Gases have their statistical ensemble. Living bodies often have the cell. Liquid water has no such fixed anchor. Its properties depend on correlations extending across multiple scales at once. Local hydrogen bonding influences intermediate range structure, and only from there do macroscopic quantities like density or heat capacity begin to emerge. That is why, in water research, structure is no longer the only language. Scientists gradually begin to speak in terms of correlation functions rather than fixed shapes, distributions rather than individual configurations, and dynamics before geometry. Perhaps that is why water has become such a special test for modern science. The unresolved questions surrounding it do not concern water alone, they also touch other complex fluids. If even liquid water resists a universal theory, then many other complex systems probably do as well. In that case, what is illuminated is not only water, but also the reason why some systems in general refuse to collapse into a reduced description. Philip Ball has suggested that this should not be seen as a failure, but as an invitation to rethink what should truly count as an explanation. and how theory ought to be built when the object of study is neither simple nor possessed of durable order. And liquid water lives exactly in that difficult middle ground. It is not chaotic enough to be ignored. It is not ordered enough to become easy to solve. It exists in a state of continuous reorganization, where patterns are only temporary, correlations are statistical, and structure itself stands perpetually at the edge of change. Perhaps that is precisely what makes water, despite being so utterly ordinary, one of the most instructive, unsolved problems in physics. Perhaps the hardest thing to accept about water is that no single level of description is powerful enough to stand alone. There is no privileged scale here. No level can be ignored, yet none fully dominates. And it is precisely this almost scale-free character that forces theory into trade-offs. Focus on local structure, and one risks losing the longer-reaching correlations. Focus on bulk averages, and the subtler structural motifs blur away. Put all the emphasis on dynamics, and thermodynamic consistency may come at a cost. Every model therefore captures one part of the truth while obscuring another. From that perspective, it is no longer surprising that decades of research have brought refinement without closure. On the contrary, the more tools we gain, the more layered water appears. New experimental techniques reveal ever finer temporal structure. New simulations extend our view toward longer-range correlations. Each advance loosens some knots while exposing others buried deeper underneath. From the perspective of complexity theory, this is almost the expected trajectory. Complex systems rarely surrender to one final, singular explanation. They usually open themselves only through multiple overlapping descriptions, each truly valid only within its own domain of application. So what is changing is not only the model of water, but the very idea of what it means to understand water. Instead of hunting for one decisive model that explains everything, researchers increasingly move toward mapping regimes of behavior. Under these conditions, these approximations work. Under other conditions, different descriptions become more appropriate. And then the transition regions between those regimes become objects of study in their own right. At that point, water no longer appears as a single object with an unchanging core, but more like a system of context, a thing whose physical meaning shifts with the domain of conditions under consideration. I think that also helps explain why disagreement among experts remains so persistent. They are not necessarily talking about the same question. One is looking at one scale, another is anchored to a particular phenomenon, and someone else is building a model for an entirely different purpose. Those models do not align perfectly, not because one side is right and the other wrong, but because they were never born to coincide completely in the first place. In the case of water, disagreement is not noise, it is data. It tells us that every attempt to compress water into a single explanatory framework will inevitably lose something essential. That resistance is very easy to mistake for a failure of science to finish telling the story. But in fact, it may be a sign of maturity. The simpler problems tend to be solved first. The problems that remain are the hard ones. And water sits exactly at the intersection of many fields: physical chemistry, condensed matter physics, statistical mechanics, biophysics, geophysics, planetary science. Each discipline brings a useful set of tools. None holds final authority. This slows convergence, because concepts do not always translate smoothly from one field to another. Terminology shifts in meaning, and models optimized for one domain can become clumsy in another. But paradoxically, that very diversity is useful. It keeps multiple perspectives alive and prevents the field from closing too early around a temporary framework that only appears convincing enough. At a deeper level still, water unsettles an assumption that science rarely questions openly: the assumption that nature, at every scale, must ultimately be describable by simple and unified expressions. Complexity theory suggests another possibility. There are systems whose behavior cannot be compressed without losing essential features. That does not make them unknowable. It merely changes the form knowledge takes. Understanding then no longer resides entirely in one equation or one model, but exists as a network of constraints, tendencies, patterns, and limits. We know what can happen, what is likely, and what is ruled out. In the case of water, that kind of understanding seems far more appropriate, because in truth, science already knows a great deal about water. It knows its anomalies, its phase diagram, its role in life and climate. It predicts many outcomes with high reliability. What has not yet been unified is not water's behavior, but the integration of all those behaviors into one shared framework. Why do so many anomalies cluster together? Why can very small changes propagate across so many scales? And why does the hydrogen bond network produce both stability and flexibility at once? These questions do not seem like simple gaps merely waiting to be filled with more data. They look more like signs of a boundary, the boundary between what can be reduced and what must be treated as a complex system. Recognizing that boundary is not surrender to ignorance. On the contrary, it is also a form of understanding. It allows science to keep moving forward without preserving the illusion that every system must eventually collapse into a neat summary. It makes room for richer descriptions, willing to accept complexity rather than flatten it away. After all, water is not misbehaving. It is simply behaving exactly as a densely interactive system, operating across many scales, would behave. And perhaps the deepest lesson lies there. Sometimes the most familiar substances draw the sharpest boundary around the reach of explanation, not because they are strange, but because they sit exactly where simplicity begins to give way to complexity. Perhaps that is also why water keeps revealing more. It is studied so much not because it is simple, but because each layer of understanding opens yet another underneath it. In that gradual opening, science is not touching failure. It is touching the quiet edges of what it can fully resolve. And then, the moment water is pushed beyond the narrow window of everyday conditions, everything changes again. Most of our experience with water takes place within a very small slice of possibilities. Temperatures between freezing and boiling, pressures close to those at Earth's surface. Even within that tiny band, water is already strange enough. But beyond it, the strangeness does not diminish. It multiplies. Under high pressure, water does not follow a simple path from liquid to solid. Instead, it opens into a branching landscape of phases, each with its own structure and properties. In the extreme regime, the phase diagram does not tidy itself into simplicity. It becomes more elaborate. The first signs of this came from experiments that compressed water and ice far beyond ordinary conditions. As pressure rises, the familiar form of ice gives way to denser crystal structures. Molecules rearrange, hydrogen bonds shift, entirely new lattices appear. Each phase occupies its own region of temperature and pressure, and the transitions between them are sometimes abrupt, sometimes gradual, depending on the conditions. The end result is not one extreme version of water, but an entire family of different states. At still higher pressures and temperatures, water enters a more unusual domain, the supraionic state. In this phase, the oxygen atoms form a relatively fixed lattice, while the hydrogen ions move through that lattice freely, almost as if the material were both solid and liquid at the same time. Supraionic water conducts electricity efficiently. The hydrogen ions behave more like a fluid than like parts locked into a crystal, while the oxygen framework retains order. This is not just a metaphor. It is a distinct physical state, predicted by theory and supported by high-pressure experiments and simulations. By Earth standards, the conditions required for supraionic water are extreme, pressures millions of times greater than atmospheric pressure, and temperatures of thousands of degrees. They do not exist at Earth's surface, but elsewhere they may. Studies of planetary interiors suggest that deep inside ice giants such as Uranus and Neptune, such states of water may be present. Beneath the visible atmosphere lie layers of matter where water, ammonia, and other volatiles are compressed and heated far beyond anything familiar to us. There, water may exist not as a liquid ocean or a solid sheet of ice, but in supraionic form, participating in the generation of unusual magnetic fields and governing heat transport in the interior. That possibility alone forces us to see water differently, no longer merely as a surface condition associated with habitability, but as a major structural component of planetary interiors. When strongly compressed, water does not merely change state. It begins to renegotiate the very boundaries that once seemed so familiar. Hydrogen bonds shorten, then reorganize. Molecular identity becomes less distinct. The classical lines between solid, liquid, and plasma no longer remain neatly separate. Phase boundaries shift, overlap, and branch. So under extreme conditions, the phase diagram of water does not simplify. It opens outward, becoming denser, more intricate, more forked, as if the more completely water is pushed to its limits, the more it refuses to become simple. That sets water apart from a great deal of other matter. Many substances, if heated enough, eventually end up as gas. If compressed strongly enough, many materials collapse into dense solids. Water refuses that monotony. It always seems to find another way to arrange itself, and each time it does, some deeper part of the underlying mechanism comes into view. There, hydrogen bonding is in constant competition with electrostatic interaction. Molecular geometry struggles against compression. Thermal motion tries to break order apart just as pressure is forcing order back in. Out of those opposing pulls, an entire spectrum of rich behavior is born. So, pushing water to extremes has never been merely an exercise in laboratory curiosity. Under such conditions, familiar assumptions are stripped away, and the interactions that truly matter begin to stand out. The supionic state is a particularly sharp example. It exposes the dual nature of hydrogen in water: light, mobile, and only relatively weakly held in place. Under compression, hydrogen responds to pressure and temperature differently from oxygen, and that asymmetry becomes so pronounced that one can see clearly how mass and bonding character shape collective behavior. But reaching such regimes is anything but easy. One must use diamond anvil cells to compress tiny samples to enormous pressures. High-powered lasers must deliver violent pulses of energy, and then every measurement has to be made almost instantaneously before the sample escapes that state or transforms once again. Even so, the results continue to accumulate. Little by little, they show that water's adaptability extends far beyond the boundaries of ordinary experience. Even when forced into regions that experiment can barely control, water continues to reorganize itself. The significance of this does not stop with basic physics. In planetary science, the high-pressure phases of water help explain how magnetic fields are generated, how heat is transported through planetary interiors, and how deep internal structures are arranged. The unusual magnetic fields of Uranus and Neptune, tilted and offset from their centers, may carry the signature of electrically conducting layers of supionic water buried deep inside. Looking beyond the solar system, the story expands even further. Many exoplanets that have been discovered are larger than Earth but smaller than the gas giants. Inside them, there may exist enormous masses of water in phases completely unfamiliar to us. In that case, habitability, magnetic shielding, and even geological activity may all depend on how water behaves under such conditions. The farther one looks, the clearer it becomes that water under extreme conditions does not merely enrich the catalogue of phases, it forces us to reconsider the very way we classify matter. Phase diagrams are often taught as clean maps, with a few clear regions and a few tidy boundaries. For water, that image is too cramped. Its phase diagram resembles a tree that keeps growing new branches. The wider the range of conditions explored, the more new branches appear, the more blurred the boundaries become, and the more states begin to overlap. Here, pushing the system farther does not eliminate anomaly. It reveals new anomalies. That is why the deeper value of extreme condition research lies not in listing how many phases can be named, but in the way it forces the right foundational questions. Under compression, which interactions truly dominate? How does hydrogen bonding adapt? At what point does molecular identity remain intact? And at what point does it begin to dissolve? These extreme regimes are like stress tests for theory. Models that work well under near-ordinary conditions may fail once pressure rises high enough. Familiar assumptions become useless. Unseen behaviors appear and demand explanation. In that sense, the extreme is where discovery is activated. What is remarkable is that the most familiar properties of water and its strangest states are not separate stories. They belong to the same continuous thread. The tendencies that make ice float are the same tendencies that allow water to enter supersonic forms. The hydrogen bonds that shape liquid water can, under compression, reorganize into entirely new architectures. That continuity matters. It reminds us that to understand water fully, we cannot look only at the mild middle ground where Earth's oceans exist. Its full character emerges only when it is examined across the entire range of what it can be. And seen from that perspective, our oceans suddenly take on a different aspect. They occupy only a narrow, somewhat fortunate corner within water's vast phase space. Liquid water at moderate temperature and pressure is not the universe's default state. It is only one possibility among many. That realization sharpens the questions about water elsewhere. Among all the forms water can take, which ones truly matter for life, for geology, for planetary evolution, which behaviors are essential, and which are merely contextual accidents? Extreme condition research does not answer those questions directly, but it gives them a frame. By showing how water behaves when pushed far beyond the familiar, science gains a foothold for understanding why its everyday behavior is so distinctive. Not because it is absolutely unique, but because it sits exactly at the crossroads of many competing tendencies. That is why water under extreme conditions is not a side story. It is the natural continuation of the same story. Every new phase discovered only expands understanding. It does not close it. Every extreme reveals another face of a substance that consistently refuses simplicity. From samples squeezed between diamond tips in the laboratory to layers of matter deep inside planets, water continues to show the same quality: adaptive, intricate, and always capable of surprise. And once our view leaves Earth, the meaning of all this grows wider still. Water is not merely a local substance, it is a cosmic material, shaped by pressure, heat, and time throughout the universe. So, understanding water under extreme conditions is not a detour away from the story of the water around us. It is still the same story, simply being told on larger scales. And then, that story must go farther still, beyond planets themselves. Water was not born on Earth. This is not a philosophical remark, but a chemical fact. Hydrogen and oxygen, the two elements that make up water, were created in different astrophysical settings long before any planet existed. Hydrogen appeared in the earliest moments after the universe began. Oxygen came later, forged in the interiors of stars and then released through stellar winds and supernova explosions. Water, as a molecule, formed only wherever those elements met under the right conditions to bond. To ask where Earth's water came from is to trace that history backward, not only through space, but through time. And it is here that astrochemistry enters the science that follows how molecules form, survive, and change in space. The farther water is pushed beyond the familiar, the more I feel we are not simplifying it, but forcing it to reveal the full extent of its nature. On phase diagrams that are often taught like neat little maps, water refuses to follow that pattern. With water, the diagram does not collapse into something simpler under extreme conditions. It branches. Boundaries shift, multiply, overlap. Distinctions that once seemed secure between solid, liquid, and plasma begin to blur, as pressure rises enough to shorten hydrogen bonds and drive them into new arrangements, while molecular identity itself no longer retains the crisp outline it once had. Many kinds of matter, when driven to their limits, gradually move toward monotony. At very high temperatures they become gas. At very high pressures they collapse into dense solids. Water refuses that fate. It keeps finding new ways to organize itself. There, hydrogen bonding competes with electrostatic force. Molecular geometry struggles against compression, and thermal motion breaks order apart at the very moment pressure is trying to impose it. It is precisely that tension which produces so many different outcomes, and each new phase that appears is like a clue, pointing toward whichever interaction is truly governing the material at the deepest level. For that reason, studying water under extreme conditions has never been mere academic curiosity. When familiar assumptions are stripped away, what remains is the underlying physics. We begin to see which interactions truly matter and which only seemed important under ordinary conditions. Supersonic behavior is an especially vivid example. It exposes the double nature of hydrogen in water: lighter, more mobile, more weakly bound than oxygen, and therefore responsive to temperature and pressure in a different way. Under compression, that asymmetry becomes more and more visible, as if mass and bonding together were rewriting the collective behavior of the entire system. But to see such things, experiment has to enter a regime that almost always resists the observer. Diamond anvil cells compress tiny samples to enormous pressures. High-powered lasers strike them with violent pulses of energy. Every measurement has to happen extremely quickly, before the sample escapes the state just created or transforms again. Even so, the results continue to accumulate, and together they point toward one conclusion: water's capacity for reorganization extends far beyond all ordinary experience, even into regions where experimental control itself has become remarkably fragile. The significance of this reaches beyond the laboratory. In planetary science, the high-pressure phases of water help explain the generation of magnetic fields, the flow of heat, and even the internal structure of planets. The unusual magnetic fields of Uranus and Neptune, tilted and offset from their centers, may be influenced by electrically conducting layers of supersonic water deep inside them. On a larger scale still, in models of exoplanets, water under extreme conditions becomes a variable that cannot be ignored. Many worlds have been discovered that are larger than Earth but smaller than the gas giants. Inside them may exist enormous quantities of water in phases completely unfamiliar to us. The habitability of those worlds, their magnetic shielding, even their geological activity, may all depend on how water behaves in such environments. What strikes me most is this: the more water is pushed to extremes, the less it sheds its anomalies. On the contrary, it reveals new ones. That is why the value of these studies does not lie in cataloging phases like collecting labels, but in tracing things back to principle. Under compression, which interaction becomes dominant? How does hydrogen bonding adapt? When does molecular identity still survive? And when does it dissolve? Extreme conditions become a stress test for theory. Models that work well near environmental conditions may collapse when pressure rises. Old assumptions stop holding, and new behaviors force science to begin explaining again from the ground up. In that way, the extreme does not separate water from its familiar properties, but connects them along a continuous line. The very tendencies that once made ice float on water are also the tendencies that allow water to enter the supersonic state. The same hydrogen bonds that once organized liquid water now restructure themselves under pressure into wholly new architectures. That continuity is remarkable. It shows that water cannot be understood merely by looking at the middle region, where temperature and pressure are moderate, where human beings feel at ease. The full character of water appears only when it is observed across the entire range of its possibilities. And when seen that way, Earth's oceans suddenly become much more modest. They occupy only a narrow but fortunate niche within water's vast phase space. Liquid water at moderate temperature and pressure is not the universe's default state. It is only one option among many others. That realization sharpens the questions about water elsewhere. Among all those possible forms, which ones matter for life, for geology, for planetary evolution? Which forms are essential, and which are merely contingent? Extreme condition research does not answer those questions directly, but it reframes them completely by showing what water will do when pushed far outside the familiar. In doing so, science understands more clearly why the ordinary behavior of water is so special, not because it is solitary, but because it sits exactly at the crossroads of many opposing tendencies. Water under extreme conditions, then, is not a deviation, it is a continuation. Each new phase discovered does not close the story, but expands it. Each extreme reveals yet another face of a substance that consistently refuses simplicity. From compression experiments in the lab to the deep interiors of planets, water retains that same quality: adaptive, intricate, unpredictable. And once our view leaves Earth and turns outward, the meaning of these discoveries becomes wider still. Water is not merely a local material, it is a cosmic substance, shaped by pressure, heat, and time throughout space. Even its origin does not begin here. This is not a philosophical statement, but a chemical one. Hydrogen and oxygen, the two components of water, were forged in different astrophysical settings long before planets appeared. Hydrogen formed in the earliest moments after the universe began. Oxygen came later, produced in the interiors of stars and released through stellar winds and supernova explosions. Water itself could form only in places where conditions allowed those two elements to meet and bond. So if we want to understand where Earth's water came from, we have to trace that history backward, not only through space, but through time. And it is astrochemistry that provides the tools for that journey. The field that studies how molecules are formed, persist, and evolve in space. If we look on cosmic timescales, the favorable niche that Earth currently maintains for water is not stable at all. I think that is a very necessary perspective for softening the sense of familiarity the oceans tend to evoke. This planet's water inventory has most likely changed over time. Some of it has escaped into space, some has been locked into minerals, and some has passed through deep recycling cycles within the mantle. So the oceans we have now are not a permanent feature of Earth, but only a moment held within a much longer flow of change. Looking outward makes that feeling even clearer. Water existing beyond Earth does not mean it will appear in the form we recognize on our own planet. Its mode of existence changes, its history changes, and its role changes as well. Every environment forces water to behave differently, and each time it does, another aspect of a substance already known to be extraordinarily adaptable comes into view. Astrochemistry shows that the formation of water is not rare, but planetary science shows that keeping water is the hard part. And it is precisely in the space between those two truths that the story of habitability begins. Isotopic traces allow us to reconstruct part of that history, but never all of it. There will always be information permanently lost to mixing and to time. That does not lead to pessimism. It simply reminds us of the vastness of the context through which water moves. From interstellar clouds to planetary oceans, that journey stretches across billions of years. Along the way, chance encounters and physical constraints together shape the outcome. And where life appears, it does not exist outside those constraints, but emerges from within them. For that reason, when speaking about water beyond Earth, the more important question is no longer simply whether water is present. The question has to be, how does it behave? How long does it persist? And under what circumstances does it remain in an accessible state? Questions like these do not give us neat answers. They only open ranges of values, probabilities, and limits. But it is precisely in that zone of uncertainty that water's true role in the universe becomes clearer. Not as a guarantee of life, but as a precondition, something that may open the door without deciding what will pass through it. Water is common, ancient, and persistent, but liquid water stably existing in contact with a complex chemistry is rare. That distinction sharpens both scientific curiosity and our perspective, especially as attention moves away from familiar oceans and toward the vast and very different reservoirs of water beyond Earth, each carrying its own unfinished history. After all the uncertainties, debates, and open questions, it is probably worth pausing to say clearly what is no longer in doubt. Water may still resist a fully complete theoretical description, but it is not mysterious in the sense of being poorly measured or loosely understood. On the contrary, many of water's properties belong among the most precisely determined in all of science. The real difficulty does not lie in a lack of data, but in having to distinguish between what has been firmly established by experiment and what still requires interpretation. There are facts about water that stand on very solid empirical ground. They have been repeated by many different techniques, in many different laboratories, over long periods of time, and do not depend on any single model or assumption. The molecular composition of water is one such certainty. Each molecule consists of 2 hydrogen atoms bonded to 1 oxygen atom in a bent geometry. The bond angle, bond lengths, and electronic structure have all been determined with very high precision. Spectroscopy, quantum calculations, and scattering experiments all converge on the same picture. Water's polarity is also established so firmly that there is almost no room for dispute. The uneven distribution of charge within the molecule has been measured directly and also inferred from countless independent observations. This feature is what underlies its dielectric behavior, its power as a solvent, and the way it interacts with electric fields. Its existence and importance are not matters still under debate. The same is true of hydrogen bonding. The directional and transient attractive forces between neighboring water molecules are supported by spectroscopy, neutron scattering, and thermodynamic measurements. The typical strength and lifetime of these bonds are fairly tightly constrained, even though the picture becomes much more complex once one moves up to the level of collective behavior. At the macroscopic scale, the certainty is even clearer. Density, heat capacity, compressibility, surface tension, boiling point, these quantities for water are known with extraordinary precision. Water's density maximum near the freezing point, its expansion upon freezing, and its unusually high heat capacity are not theoretical ideas. They are repeatable measurements. The same is true of water's phase behavior across many regions of conditions. The existence of multiple ice phases under different pressures, the conditions for supercritical water, and the broad shape of the phase diagram are all supported by decades of experiment. Even though details continue to be refined, the large-scale structure of that picture is basically stable. In biology, a similarly strong consensus exists. Water is the solvent for biochemical reactions, stabilizes charged and polar groups, supports proton transfer, and regulates temperature. Those functions are not merely inferred, but have been demonstrated across living systems, from the level of enzymes to entire ecosystems. Caution becomes necessary only once we move from observation to interpretation. Knowing that hydrogen bonds exist does not mean we have uniquely determined how they are arranged at every moment in liquid water. Knowing water's macroscopic properties also does not mean we have uniquely traced them back to one single microscopic configuration. Different models can still explain the same set of observations equally well, and that is exactly where the debate remains alive. For example, there is broad agreement that liquid water possesses short-range order, but which description of that order is the most useful one, that is still not settled. Perhaps the most striking thing about the science of water is not that people are still debating it, but that they know very clearly what they are debating. For liquid water, there is no shortage of microscopic pictures that have been proposed. Some see in it local structures that resemble ice. Others focus more on density fluctuations, or on the degree of connectivity within the hydrogen bond network. It seems to me that each approach touches part of the truth, yet none has the authority to declare itself the whole of that truth. The deeper one goes, the more one has to accept that the same system may allow multiple descriptions to be simultaneously correct at different levels. That is also very clear when water approaches surfaces. Near biological membranes, proteins, or mineral interfaces, water no longer behaves like bulk water. Its molecules tend to become more ordered, and their motion less free. On that point, there is almost nothing to argue about. But how much farther that ordering extends, how stable it is, and what functional significance it carries, those remain under active consideration. Claims about distinct phases of intracellular water are even more delicate. Interfacial influence stands on solid ground, but extending that influence into long-lived, large-scale alternative states still remains, for now, largely in the realm of speculation. For that reason, in this field, separating what is observed from what is interpreted is almost an ethical principle, and that applies not only to experiment, but to modeling as well. No one doubts that molecular dynamics simulations can reproduce many properties of water extremely well. Nor does anyone doubt that different models still diverge in important details. But those differences are not signs that the experimental data contradict themselves. They reflect different modeling choices. There is a fairly clear consensus here. Researchers know where the limits of their models lie, even if they do not yet agree on which model is best. I think that distinction matters more than it may sound. Scientific discipline has never required that every question be fully resolved. What it requires is that one speak plainly about which claims are supported by direct evidence and which still rest on a further layer of interpretation. The science of water remains robust precisely because it does not confuse those two levels. A solid measurement is treated as solid. A provisional interpretation is recorded as provisional. Disagreement is not flattened away for the sake of neatness. It is preserved, described, examined, and then gradually constrained within tighter limits. That is how one avoids a very common mistake, confusing uncertainty with ignorance. With a substance as familiar as water, that temptation is especially strong. It is easy to think that if open questions remain, then we still do not really understand it. But with water, almost the opposite is true. The unanswered questions remain precisely because the foundational measurements are so secure. The basic facts do not waver. What is still missing is a way of connecting them into a single explanatory framework. Scientific progress often begins with description and only later moves toward explanation, and water has been described in almost extraordinary detail. The challenge now is not to keep discovering more isolated phenomena, but to understand how all those descriptions can belong to one shared picture without contradicting one another. While that picture remains unfinished, the reliability of the science of water is not diminished at all. Engineers still design systems around the properties of water with very practical confidence. Climate models still use water's behavior effectively. Biology depends on the chemistry of water almost every day. None of those fields is paralyzed by theoretical debate, because they operate on the basis of what is already firmly known. And precisely because researchers know what is certain, they become all the more careful when confronted with larger claims. A new phase, hidden order, or a universal theory of all liquid water is not accepted simply because it is appealing. The evidence has to be weighed. Alternative possibilities have to be placed alongside it. That balance between confidence and restraint is, in fact, a strength. There are systems that cannot be explained in a single layer of language, and water seems to be one of them. Even if it is never fully reduced to one unique model, that does not prevent science from making accurate predictions within defined ranges of conditions. Knowing where certainty ends is itself part of understanding, and when attention turns to the unresolved questions, that foundation becomes decisive. It keeps speculation from drifting too far, forces imagination to remain anchored to what can be measured, and reminds us that the next step forward will not come from discarding what is already known, but from building on it carefully. In the coming years, experiments may reach even faster timescales. Simulations may expand to larger systems. New theoretical frameworks may emerge, not necessarily to replace existing knowledge, but to reorganize it according to a different logic. But however the organization of knowledge may change, the core points remain fixed. Water is a small molecule with strong polarity. Its hydrogen bonds are weak when viewed one by one, but become remarkably powerful in collective behavior. Its macroscopic properties are anomalous yet measured with high precision, and its behavior both supports life and shapes planets. Those are no longer open questions. The real question lies in how all of those facts can coexist within one unified picture. And when one looks more closely at what remains unresolved, it becomes clear that these are not just scattered loose ends. They are structural questions, arising naturally from the nature of liquid water itself. The problem is not missing data, nor failed experiments. The problem is that liquid water exists precisely in the regime where familiar theoretical approaches begin to lose their footing. It is a densely interacting system. The molecules are close enough to affect one another strongly, yet also mobile enough to keep rearranging. The interactions here are directional, transient, and cooperative all at once. No single interaction completely dominates, nor does any single scale fully contain the behavior. From the standpoint of theory, that is an almost awkward position. In solids, durable order allows simplification. In gases, the weakness of interactions does something similar. But liquids and water above all occupy the region in between, where neither path can be fully applied. That is why a question even larger than water itself emerges. Can there be a unified theory of liquids, in the way physics has strong frameworks for gases or crystals? Such a theory, if it exists, would have to allow the behavior of liquids to be predicted from a small number of general principles, without depending too heavily on the molecular details of each individual system. For many decades, physics has searched for that, but progress has been uneven. Statistical mechanics has powerful tools, yet often depends on approximations tailored to each case. Integral equation theories capture some correlations, but struggle with strong directionality. Mode coupling approaches can describe dynamics near the glass transition, yet become less effective again when dealing with ordinary liquids. Water places pressure on all of those approaches at once. Its hydrogen bonding creates strong orientational correlations. Its density anomalies reflect an extremely delicate balance between competing structures, and its dynamics stretch across many timescales, with rearrangements that are collective rather than merely local. So the question of whether all those features can be gathered into a compact and unified theoretical description remains open, and not everyone is convinced that such a unification must exist. Some researchers believe that the very nature of liquids may make them resistant to any attempt to gather them into one common framework. In that view, liquids may require system-specific descriptions, each tuned to the particular type of interaction operating within it. And with water, perhaps it is exactly here that its elusiveness appears most clearly, not because it is vague, but because it is too richly structured to be easily reduced. Perhaps one of the sternest, yet also clearest, ways to look at this is the following. The absence of a universal theory of liquids may not be a temporary gap in knowledge at all, but a sign that matter in this regime organizes itself in a way that does not easily compress. If that is true, then water is not an unfinished problem merely because science has not yet gone far enough, but because the nature of the system itself places a distinctive resistance in the path of every effort at unification. Even so, not everyone is pessimistic. A cautious optimism still exists in the research community, especially in light of progress in soft matter physics, where ideas such as emergent behavior, scaling laws, and universality classes have at times helped organize complexity without erasing it. In that spirit, perhaps a unified language for liquids may still be possible, only it would not resemble the traditional image of a neat, closed theory applied uniformly to every case. What matters is that this debate is not taking place in some loose speculative zone. It is unfolding very concretely, across international collaborations spanning soft matter physics, statistical mechanics, and physical chemistry. Large research networks are bringing experimentalists, theorists, and computational scientists to the same table in order to compare data across different techniques and across different scales. Neutron scattering opens one window, synchrotron light sources open another, and ultrafast laser laboratories reveal slices neither of the other two can reach. On the other side, high-performance computing centers now allow simulations that would have been technically out of reach only 10 years ago. None of that effort is redundant. What has not yet been achieved is not data, but a way of joining all those slices into a whole that can truly stand. That difficulty of joining things together shows itself very clearly in the question of local order in liquid water. That local order exists is almost a point of consensus, but how to name it, how best to describe it, that is the real issue. Some descriptions prefer to focus on tetrahedral arrangements, as if tiny remnants of ice were always flickering inside liquid water. Others pay more attention to density fluctuations or to changes in coordination number, Some models go further, treating water as a mixture of different local environments that can transform back and forth into one another. But there are also researchers who resist precisely that kind of division, arguing that it imposes sharp categories onto what is in fact a continuous distribution. Here, the point is not necessarily to find the one absolutely correct description. The question is which description is most useful for which phenomenon, and that usefulness may very well shift with context. The same ambiguity returns when people talk about water's anomalies. Its unusual properties seem to cluster within a certain region of temperature-pressure space, yet why they cluster there is still unsettled. One interpretation sees them as traces of an underlying critical point located in a region of conditions that cannot be accessed directly. Another argues that no sharp transition is needed at all. Smooth shifts in local structure alone may be enough to produce the observed picture. Both sides have evidence, but neither has evidence strong enough to close the debate. This kind of uncertainty is not something that can be erased simply by adding a few more measurements. It is structural uncertainty, because multiple mechanisms can still generate the same macroscopic behavior. To distinguish among them, one needs not only better data but also a precise sense of what would count as a resolution in the first place. Even measurement itself has its own limits. Ultrafast spectroscopy and advanced scattering techniques can bring us very close, but what they provide are still indirect signals. Those signals must pass through models in order to be understood, and models carry assumptions. However subtle those assumptions may be, they still shape the conclusion. That circle is not unique to water, but in water, it becomes sharper because of the system's exceptional sensitivity. A very small change in conditions can leave behind a difference large enough to measure. That is exactly what makes it so much harder to draw general principles from countless sensitive responses. And then there is another layer of questions. How do molecular scale motions rise into mesoscopic and macroscopic behavior? How do local fluctuations affect bulk thermodynamics? And by what path do hydrogen bond networks that exist only briefly give rise to long-lived properties such as heat capacity or compressibility? This is the zone where dynamics and thermodynamics meet, and it is also a zone where classical tools are still being extended in order to keep up. My sense is that here, water continually pulls science toward the edge of the very toolkit it is using to study it. In biology, the situation is no simpler. The general role of water in the cell has long been established, but the details of how intracellular water participates in organization, transport, and regulation are still being actively investigated. The extent to which the structure of water directly influences biological function is not yet settled, and perhaps cannot be reduced to a single answer. This is not an accident or an arbitrary gap. The cell itself is a heterogeneous, constantly changing, and extremely crowded environment. Water inside it will naturally reflect exactly that complexity. Expecting a truly simple description may have been unrealistic from the start. Across all of these areas of research, one theme keeps returning. The open questions surrounding water do not necessarily point toward hidden secrets waiting to be uncovered. They point toward limits imposed by complexity itself, by overlapping interactions, and by differences of scale. That changes the way uncertainty ought to be understood. It is very easy to call unsolved things mysteries, as if some missing foundational piece were still absent. But with water, what may be missing is not more raw fact, but a form of explanation better suited to the nature of the system. If that is so, then the limits of knowledge are no longer walls blocking progress. They become boundaries, telling us what kind of progress is possible. The science of water, in that sense, does not advance by closing every question. It advances by tightening the constraints. Models become better bounded. Interpretations grow sharper. The range of validity for each framework becomes clearer. This is, in fact, already happening. As data accumulate, debates gradually narrow, overblown claims are restrained, and confusion gives way to disagreements that are useful and clearly bounded. The field is not drifting into vagueness. It is converging just not toward one single picture, but toward a clearer map of what can and cannot be said. That is another kind of scientific maturity. It may be that our understanding of water will never crystallize into one ultimate equation or one unified theory. It may be that what remains instead is a structured understanding of behavioral regimes, operating mechanisms, and explanatory limits. But such an outcome does not weaken science. On the contrary, it makes science more refined. Water forces us to reconsider what it truly means to explain a system. Perhaps sometimes explanation does not mean reducing everything to one layer, but accepting a chain of layered descriptions, each valid within its own scale, and linked together by careful reasoning rather than by the ambition of absolute reduction. Recognizing that does not end the story. It only changes its direction. What remains unresolved about water is not a sign of failure, nor the result of neglect. It shows that water lies exactly at the edge of what current theoretical frameworks were made to handle, and it is precisely at such edges that new ideas usually begin to take shape. So as long as research continues, water will remain a special testing ground, a place where theories of complexity, emergence, and collective behavior are continually challenged, adjusted, and then pushed farther still. Water will continue to expose assumptions that science once thought secure, and it will continue to resist overly easy summaries. Not because it is some incomprehensible thing, but because it is itself a densely interactive system, spread across many scales and never truly still. That is exactly what makes water such a deeply instructive subject. As knowledge shifts from merely collecting more fragments to trying to synthesize them, the unresolved questions stop being simple obstacles. They become the framework through which understanding can go deeper, without forcing itself into a final closure. Perhaps that is also water's most beautiful paradox. It is too familiar. It sits in the glass on the table, in the moisture of the air, in valleys carved away over time, and in every living cell. It is so familiar that it almost disappears into ordinary life. And yet that seemingly ordinary substance, as this whole journey has shown, is one of the most intensely studied things in science, and still not fully understood. That tension between the familiar and the unfinished is not evidence of failure. To me, it feels more like a very quiet lesson in how knowledge really works. Understanding does not always move straight toward a neat ending. There are systems such that the more we study them, the more knowledge opens in two directions at once, spreading outward and sinking deeper. With water, this is especially clear. Measurement becomes ever more precise. Models become ever more refined. Interpretations become ever more careful. And yet the sense of total closure never arrives. Not because some secret missing piece remains hidden, but because the system itself resists being compressed into one final summary. And it is precisely there that scientific humility becomes a real strength. Not the kind of humility that doubts known facts, but the kind that knows how to distinguish between what has been firmly measured and what has not yet been unified. The facts about water are among the most reliable in all of science. Its molecular structure, its polarity, its hydrogen bonding, its macroscopic properties, and its role in life and climate, all of these have been established with extraordinary confidence. What this humility acknowledges is not uncertainty in the data, but the distance between knowing those properties and gathering them all into one single, complete framework. Water sits exactly where many scales intersect. Electronic structure shapes hydrogen bonding. Hydrogen bonding shapes molecular networks. Those networks in turn govern thermodynamics. And thermodynamics, in its turn, enters into the behavior of planets. No one level truly governs all the others. Each takes part, each contributes to the whole. That is why an explanation of water cannot have only one layer. It must have several. One model may capture the density anomaly, another may explain dielectric behavior well, yet another may follow the dynamics of water under pressure. None is wrong simply because it is partial, but none is sufficient to declare itself the whole picture. Science moves forward, then, not by pretending that these partial viewpoints are the final word. It moves forward by holding them together honestly. That is why water has become such a valuable case study. It shows the limits of reductionism without rejecting reductionism itself. It shows that collective behavior can emerge from simple components and still not be completely reducible to them. It reminds us that complexity can still obey laws, can still be repeatable, can still be measured, even when it is not simple. In that sense, water teaches science a rare kind of restraint. It forces science to say clearly, and with justified confidence, what is known. At the same time, it also forces it to say just as clearly what remains open. It reminds us that unanswered questions are not always merely temporary gaps. Sometimes they reflect the very shape of the problem itself, and that does not weaken knowledge. On the contrary, it strengthens it. When science is willing to acknowledge its limits, it avoids false certainty. When it separates measurement from interpretation, it keeps itself anchored to reality. And when it accepts that some systems require multiple parallel descriptions, it becomes more precise, not more vague. Across many centuries, and across many different disciplines, water has continued to reward exactly that kind of approach. Every advance sharpens understanding while also revealing another layer of structure. Every refinement makes water's behavior clearer while also showing that it is not exhausted. So this is not a suspended story waiting for a final chapter. It is more like a stable but still evolving form of understanding, growing through ever more precise constraints rather than through one final victory over the subject itself. To understand water, in the end, is not to make it stand still in our hands. It is to understand how it moves, how it interacts, and how it continually resists oversimplification. In a broader sense, water is also reflecting science itself. Knowledge does not always end in completion. Sometimes it arrives at another kind of balance, knowing clearly what is known, keeping a careful respect for what is not, and having enough confidence to place both within the same frame without pretending that everything has been closed. That balance is not uncertainty. It is a form of understanding that does not require an ultimate conclusion, and for something so ordinary, perhaps that is one of the most enduring lessons water leaves behind.